Tools and methodologies. The security tools and methodologies used during a web application assessment can vary, but it's important to establish a tools and techniques baseline. In this module, we'll cover some of the more common tools and present some examples of their usage in order to set a firm foundation for web application assessment. Before we get started, it's important to clarify that web application vulnerability research can be conducted from a white box or a black box perspective. During a black box assessment, the researcher will assess the application solely from an external perspective. In order to find a vulnerability, the researcher sends specifically crafted input requests and observes the output and/or effects generated by the application. During a white box assessment, a researcher either has access to the original source code or is at least able to recover it in a near original state. Armed with access to the source code, the researcher can perform a more thorough analysis of the code and its execution flow in order to identify and exploit any vulnerabilities. In this course, we will primarily focus on white box assessment, but some of the tools and techniques, such as web traffic inspection, can be leveraged during a black box assessment as well. When dealing with an unknown web application, a researcher should first inspect the traffic generated while browsing the application's website. There are many elements a web application can present to the end user within the browser. However, before those elements reach their final presentation state, there can be many more requests happening between the client and server in the background. Web application proxies are indispensable for capturing as much information as possible about our target during this initial phase. These tools route HTTP requests generated on the client side to the destination web application while saving the intercepted traffic for later inspection and use. For the purposes of this course, we will primarily use the community version of the Burp Suite proxy. This tool not only allows us to capture relevant requests between the client and server, but also provides us with additional features that give us the ability to easily manipulate any given request in arbitrary ways. Let's take a look at the basic setup for Burp Suite. The Burp Suite tool can be launched in Kali using the shortcut located on the toolbar. Once Burp Suite is launched, we'll see a few notifications. The first one, which initially seems like an important warning, is generated because the tool does not officially run on short-term support versions of Java. However, since the Kali team always tests Burp Suite on the Java version shipped with the OS, we can safely ignore this warning. The next screen offers the option to start a new project or restore a previously saved one. The ability to use project files is a feature of Burp Suite Pro and will not be required for this course. Finally, before the proxy is fully started, we're presented with an option to load custom configurations or use the default one. This allows us to customize and streamline Burp's many options, but for now, we'll stick with the defaults. Now that Burp Suite has started, we can validate the status of our proxy server from the Alerts tab. As a final step in our setup, we need to configure our Firefox browser to use the proxy server. This can be done from the browser network settings. In the network settings window pane, we'll select the manual proxy configuration and specify localhost for the IP address and 8080 for the HTTP proxy port field. Additionally, we'll also check the Use this proxy server for all protocols option to be able to intercept every request while testing the target application. Now that Burp Suite and Firefox are set up, let's run a quick test to make sure everything is working as expected. For the purposes of the test, we'll simply use the browser to navigate to one of the dedicated virtual machines inside the lab network, which hosts a vulnerable version of the @mail web application. Rather than using the IP address directly, we've edited our hosts file in Kali so we can refer to the lab machines by name. Make sure you use the correct IP addresses found in your student control panel and then modify your hosts file accordingly. Now, let's try to browse to the AppMail server. Notice that our browser seems to hang. This happens because Burp turns on the intercept feature by default. As the name suggests, this feature intercepts requests and allows us to inspect them before forwarding them to the target. For the purposes of this test, we can safely turn off this feature. At this point, if everything went well, we should be able to inspect all requests and responses generated by our web browser and target application in the Burp Suite HTTP History tab. Modern web applications require the browser to perform many requests that may not be of any interest to us for vulnerability discovery, including requests to third-party statistics collectors. Fortunately, Burp allows us to set a collection scope to help focus only on the requests we're interested in. We can set this by right-clicking on any of the requests issued against our target server and selecting the Add to Scope option. If we do this on a top-level domain URL request, Burp Suite will add the entire domain to the scope. Alternatively, selecting a specific page will only add that single URL to our scope. For now, we only want to focus on items that are in our scope, so we'll choose Yes here. With our AppMail server added to the scope, we can now filter the HTTP requests and responses to show only in-scope items. Let's do this now. We can verify that our scope has been set properly by switching to the Target tab and then selecting the Scope subtab. Great, we're all set. When inspecting web applications, we often need to see how granular changes to our HTTP requests affect the response returned by the web server. Burp Suite makes this simple with the Repeater tool, which allows us to make arbitrary and very precise changes to a captured request and then resend it to the target. Let's see how this looks in practice by selecting the request we added to the scope and choosing Send to Repeater. As a first test, we'll press Go in order to resend our original request unmodified. This response to our unmodified request will serve as our baseline response. As we modify our requests, we'll compare the responses with this baseline. Now, let's change the language to German in the Accept Language header and see how the AppMail application responds to this change. It looks like the header response size and content length have changed. The Comparer feature of Burp Suite highlights the differences more clearly. Let's send our response to the Comparer. Now let's go back to our original response and repeat the same process. If we go to the Comparer tab now, we can see that Burp Suite has automatically highlighted the two responses. We now have the option to compare these responses for differences in words or bytes. Since we're not dealing with binary responses in this example, we'll choose the words option. As we can see, the differences are now easily recognizable. This is a very simple example that shows the power of the repeater and comparer functionalities when testing a web application. We're often confronted with encoded data in HTTP requests and responses in modern web applications. This can make data inspection and manipulation time-consuming, but fortunately Burp Suite has a versatile decoder tool. Let's see this tool in action with a basic example. We'll browse to the following AppMail URL. If we switch back to Burp Suite to review the server response, we can see a function named URL encode. The return statement shows us that some of the characters have been URL encoded and as a result, they can be more difficult to interpret. Let's highlight the return statement and send it to the decoder. In the Decoder tab, we'll click on Decode As and select URL as the URL encoding scheme. Once decoded, the text box below our original data shows the return statement, which is now a lot easier to read and understand. Up to this point, we've only demonstrated a few basic but very useful features of Burp Suite. This tool contains many more features that can be very helpful when researching complex web applications. Be sure to check out the official Burp Suite documentation for further information. The requests library is one of the most popular Python libraries used to interact with a web application. Let's take a look at a simple script to demonstrate how requests can be used. First, we import the requests library. On line 4, we disable the display of certificate warnings. This helps avoid excessive warnings while issuing requests to websites using insecure or self-signed certificates. The format text function prints the response headers and body to standard output in an organized way. On line 13, the R variable is set to the result of a GET request to the Manage Engine web server in the labs. In the request, the verify flag is set to false. This prevents the library from verifying the SSL TLS server certificate, which in this case is self-signed. Finally, lines 14 to 17 demonstrate how to inspect a few common components of an HTTP server response. Let's run the script to confirm that it's working properly. Good. As you can see, the request was successful, and we were able to access various parts of the HTTP response by accessing the properties of the Python request object. We can also use the request's built-in proxy support to help debug the HTTP requests and responses while running our scripts. To do this, we simply add a Python dictionary object specifying the proxy details. Let's test this by modifying our previous simple example script. Now, let's run this and locate the request in Burp Suite's Proxy History tab. However, we still only see requests to the AppMail server. This is because we have not added Manage Engine to our scope. We can re-enable the logging of out-of-scope items by clicking the Re-enable button and run our script. Then we can proceed to add the Manage Engine server to our scope. Now we should be able to see the requests in the HTTP History subtab. Great! While this is a simple example, this script provides us with a starting point for the proof of concept scripts we will develop in the upcoming modules. The ability to recover source code from applications written in a compiled language is extremely valuable when conducting web vulnerability research. During this course, we'll focus mainly on Java and .NET source code recovery, since they're common and our vulnerable applications are written in these languages. For source code recovery of .NET applications, we'll use the freely available dnspy decompiler and debugger, as it provides us with all the functionality required for this course. Let's create a simple C# example program to demonstrate a very basic workflow that can be used when dealing with .NET executables. We'll remote desktop to the DNN virtual machine where dnspy is already installed, paste the C# application source code into a text editor, and save this file as test.cs. Our application simply asks what our favorite web application language is and echoes the answer to the console. In order to compile it, we'll use the CSC compiler from the .NET framework. Great, let's execute it to make sure it works. We can now open dnspy and attempt to decompile the test application. In order to do that, we can simply drag and drop the executable onto the dnspy window. Let's now explore the source code of our executable file by expanding the application name in the Assembly Explorer pane. Once we select the Program class, we should be able to see the decompiled code. Excellent. The decompiled code appears to be identical to the original source. Let's now check out some more advanced features. When dealing with more complex applications, one of the most useful decompiler features is the ability to find cross-references to a particular variable or function in the codebase. This can allow us to get a much better understanding of the application code logic. Since one of the course modules focuses on a .NET Nuke web application, let's suppose that during analysis we noticed a few base64 encoded values in the HTTP requests captured by Burp Suite. In order to better understand where these values are decoded and processed within DNN, we could assume that the function or functions that handle base64 encoded values contain the string base64 in their name. Let's start by searching for this term in the decompiled DNN code using dnspy. Normally, for a thorough analysis, we should open all the .NET modules loaded by the web application in dnspy. However, for the purposes of this demonstration, we'll only open the main DNN module, .NET-Nuke.dll. Since we're only interested in functions, we'll apply a filter to locate the string within method names. Excellent. We found a few results. Let's try analyzing the base64 URL decode method by right-clicking on it and choosing the Analyze option. We should see the results of this action in the Analyzer window. Specifically, if we expand the method name, we see two options, Used By and Uses. Furthermore, if we expand the Used By node, we should see all of the places where our method is called within the target DLL. If we now click on a cross-reference, we can see where the function call is issued in the source code. This technique can be extremely useful when analyzing source code. dnspy also has the ability to arbitrarily modify assemblies. This can come in handy if we need to add debugging statements to a log file, for example. This also gives us the ability to alter assembly's attributes in order to better debug our target application. In order to demonstrate this technique, we'll return to our previous custom executable file and edit it using dnspy. Let's right-click on the Program class and choose the Edit Class option from the context menu. We're going to try to change the portion of the string that says "Your answer was." Once the change has been made, we click the Compile button. After we've completed the module, we need to save the file, overwriting the original. If we go back to our command prompt and rerun test.exe, we'll see that the second print statement shows the modified text version. Great. Using a very basic example application and DNSpy, we were able to demonstrate how to recover and alter the code of .NET applications. There are many tools capable of decompiling Java bytecode. For the purposes of this course, we'll use the JDGUI decompiler. Java-based web applications primarily consist of compiled class files that are compressed and grouped together into a single Java archive or jar file. Using JDGUI, we can extract the class files and decompile them back to Java source code. To demonstrate the usage of JDGUI, we'll make an example jar file and then decompile it. Let's do this on our Kali Linux virtual machine. We'll create a jar directory and create a simple Java file within it. This simple Java application asks the end user what their favorite language is and prints the answer out to the console. As part of the compilation process, we have set the Java source and target versions to 1.8, which is the current long-term suggested version from Oracle. Now we should have the compiled file named test.class in our directory. In order to package our class as a jar file, we'll need to first create a manifest file. This can be easily accomplished by creating a manifest.mf file within a directory named meta-inf. The manifest file must contain a reference to our test class file. And now we're ready to create our jar file. Good. Let's run our example class to make sure it works as expected. Now that we've confirmed that our jar file actually works, let's copy it to the Manage Engine virtual machine where JDGUI is already installed. We can do this quickly by setting up an SMB server on our Kali Linux virtual machine. The impacket SMB server script will do the trick. With the Samba server running, we can RDP to the Manage Engine virtual machine and transfer the file. Now let's decompile our Java bytecode. We'll open JDGUI from the taskbar and drag our target file on its window. We should see the contents of the jar file, and using the navigation pane on the left, we can reach the decompiled source code of our test class. Nice. Now we can see the decompiled source. This concludes our very basic review of some of the tools and techniques used during a web application assessment. We'll leverage these tools and dig deeper into these techniques in the course modules that follow. @Mail Mail Server Appliance, from cross-site scripting to remote code execution. The @Mail appliance is built as a complete messaging platform that contains web interfaces for reading email and server administration, providing a rich web environment and, most interestingly, a large attack surface. In this module, we'll cover the analysis and exploitation of a stored cross-site scripting vulnerability in @Mail that can be used to gain access to an authenticated session. After gaining admin privileges through XSS, we'll escalate the attack by manipulating global configuration settings with the goal of lowering the default security posture of the application. This will ultimately allow us to upload arbitrary files, resulting in remote code execution on the target system. The @Mail webmail system has two different but similar web interfaces, one for webmail and the other for administration. Refer to your course materials for the credentials to both the webmail and administration interfaces. To make our attacks easier, we've updated the host file to point the @mail hostname to our target vulnerable server. Let's log in and validate that the server is working properly. This URL is the webmail login for @mail. We're going to log in with the admin account, but it's important to note that we're only logging into the webmail of the admin account. The administrative features are found in another URL, which we'll validate in a moment. The account we'll use to log in is admin@offsec.local. The password we use here is 123456. Okay, we see a very typical webmail inbox and all the expected functionality. Now, let's sign out and validate the administrative interface. The URL for the administrative interface is slightly different, replacing mail with admin. For this interface, we'll use the username admin and password admin. Here we see the administrative functionality that's used to manage the @mail instance and other status tools that you'd expect from a mail appliance. We'll sign out and move on to vulnerability discovery. We'll start conducting our analysis by attempting to detect XSS vulnerabilities with the help of a fuzzing tool. As with many web application vulnerabilities, XSS relies on the fact that user input is not properly validated and sanitized before being displayed to the end user. If sanitization is not implemented or it is incomplete, the reflected user input can result in code execution. Although there are many publicly available XSS fuzzing tools, we developed our own extensive and easy-to-use XSS fuzzer that targets web-based email clients. Our plan is to send emails to the admin email account with malformed fields. Then we'll log into the webmail interface as the admin user and analyze the emails through our web browser. The @mail SMTP server does not require authentication for relaying of local messages, so we can use it as the outgoing server in our fuzzer to send our malformed emails. Let's quickly run this script and see what the options are. Passing the -L option to XSS webmail fuzzer.py will result in a list of available payloads for the cross-site scripting attacks. In order to minimize the number of emails and to hopefully uncover an XSS vulnerability quickly, we can start by injecting individual payloads using the -R option into common email fields. We'll start by choosing payload number 2, script tag with alert. Here we're sending emails to the admin@offsec.local account using the T flag. Next, the F flag is the from email address, which we set to attacker@offsec.local. The S flag designates the SMTP server, and the C flag specifies the connection type. In our case, it will be a plain or unencrypted connection. Next, we have the J flag for the injection type, and here we've selected 1x1 main, which will inject malformed input iterating through all the email headers. Lastly, we're using the R flag or replay option to inject a specific payload from the list we viewed earlier. Now let's run the script and send some XSS payloads to the admin account. Once the fuzzer is finished sending the payloads, we can log into the webmail interface to see if any of our emails trigger a pop-up message, indicating that we identified an XSS vulnerability. Looking at the first email, we see that the script alert injection in the body email header was not successful. Let's open a few more emails and see if we get an alert. Look at that. Here on the third email, we have a successful cross-site scripting pop-up. Looking at the email details, we find that this was an injection into the date field. As you can see, we generated quite a few emails and will continue to do so through this module. In order to make sure that we're always looking at the correct email, we'll use a handy Python script to clean up the inbox between fuzzing sessions. You'll find this script in your course materials. Okay, Now let's check our inbox to see if the cleanup script worked correctly. Great! Now we have a quick way to send test emails and easily clean up after ourselves. As a result of our first test, we discovered that the email date field can be injected with JavaScript. Usually, finding a vulnerability like this means that we're likely to discover more. We'll run the fuzzer again, this time with payload number 13, which will attempt to inject an iframe into the email headers. Now let's check our inbox and see what payloads worked. We immediately see a working payload here in our first email. Let's check the others. Similar to our first test, more JavaScript pop-ups appear from payload 13, iframe injected in body, and iframe injected in date, which again suggests these fields are not properly sanitized. At this point, we have at least a couple different injection points. Our next step is to develop a proof of concept script. In the course materials, you'll find an example script. Let's take a look at it now. Our script first determines a function named sendMail. This function takes 4 arguments, which are the equivalent of toEmail, fromEmail, SMTP server, and cross-site scripting payload. The function then creates the message variable, which contains both the headers and the body of the email. On line 8, we can see that we're injecting the payload into the date field. We connect to the SMTP server and then send our malicious email on line 17. Next, on lines 26 and 27, we see that the destination email and from email variables are set. The SMTP server and payload are set from command line arguments, which are used to call the sendMail function. Let's use this script to send a cross-site scripting payload injected into the email date header field. First, let's make sure we empty the inbox. Great, now let's send our payload. Finally, let's check the email inbox to see if our new script worked and sent a malicious email. Excellent, our script works. Now that we have a proper tool in place, we can focus on more sophisticated attacks. Next, we'll change our attack from triggering a message box containing the number 1 to displaying something more useful. A very typical attack in cross-site scripting is to steal a user's session cookie, which can allow an attacker to visit a website authenticated as the victim user. In JavaScript, the document object represents all the HTML code that would be rendered within a window. The cookie property of the document object allows JavaScript to read, create, modify, or delete cookie data. We can access the cookie property in JavaScript by using the syntax document.cookie. Let's try this using our new payload script. First, we'll empty the inbox using our cleanup script. We left the alert as the method to display the cookie, and within the alert, we use the cookie property by adding document.cookie. Let's send this and see how it works in our browser. Excellent. Now that we know how to use the cookie property within JavaScript, let's move on to see how we can use the cookie data. Depending on any session protection mechanisms, we now may have the ability to steal cookies and session information. This would allow us to impersonate our victim and access their webmail from different locations without having to authenticate. This is known as session hijacking, and it's a very common attack in web applications. To implement this attack, we can either choose the date field and inject malicious JavaScript, or an iframe, or the body field, which only allows for the use of an iframe. If we can gain control of a targeted session, we should be able to perform arbitrary actions all in the role of the legitimate owner of the account. For example, we could read emails, send arbitrary emails, delete any emails, enable mail forwarding to any address under our control. We could even access all the contacts, which is useful for spamming, enable auto reply, or exploit any authenticated server-side application security flaws we might find. First, let's see if we can actually retrieve cookies from a remote location and hopefully stay undetected. In order to make our attack as discreet as possible, we'll use a payload that will call a JavaScript file named @mailsession.js that is hosted on our attacking system. This file contains code that will allow us to retrieve the session cookies. Let's open that file now. Okay, let's explain what we have in this JavaScript file. In the addTheImage function, the img variable is set to the createElement method of the document object. This method creates HTML elements, and in this case, we pass img as the tag name, which is an HTML tag for an image. In the next line, we set the source property of the img element to point to our attacking server. We need to change this field, and in our case, our attacking machine's IP is 192.168.119.15. After our IP address and port number, 9090, we append the document.cookie property. On line 4, we're appending the image tag to the body of the HTML document, and on line 7, we call the addTheImage function. In order to complete this attack, we need to set up a simple web server that will host the @mailsession.js file. Then, we need to send a malicious email with a payload that references our @mailsession.js on the attacking server. Let's set up the web server first with the simple HTTP server Python module. The web root for this HTTP server will be in the current working directory where this command is executed. Great. Now that we have our server running, let's send the payload. Let's check our inbox in the browser. Okay, nothing seemed to happen, but let's check our server. Excellent. Once the payload executes on the victim's browser, we find that the JavaScript code attempted to retrieve a non-existent URL, and the end of this URL disclosed the session cookie of the logged-in user. Now that we've stolen the cookie, we need to see if we can hijack the session with it. First, let's clear all the cookies in the browser. Let's navigate to About:*Preferences. We'll click Privacy. Then we'll select Clear Your Recent History or Clear All Current History. We'll make sure everything is selected and that all checkboxes are selected. Finally, we'll click Clear Now. Now let's restart Firefox and browse to the mail interface again. Then let's open the developer toolbar. In the console, we can use the same method to set a cookie that we used to obtain one. We'll just set document.cookie equal to the cookie value we obtained. Now let's go get our cookie value and copy it to the clipboard. And we can paste the cookie into the JavaScript console. Good. We just set the cookie for this page, so let's refresh and see what happens. Excellent. We have successfully stolen the cookie and used it to hijack an existing session. Let's look into other ways to take advantage of a logged-in user. Since we're targeting an administrative @mail user, we could have unrestricted access to the application. However, we've successfully hijacked the admin's @mail session. We will only be able to impersonate the target user as long as the session is alive. In other words, if the admin user logs out, the cookie will be invalidated. This prevents us from accessing the admin interface and finishing whatever attack we planned. Instead of performing our attack from the browser, we could consider a more robust method and automate our actions with the help of a script. For example, our script could process the request issued through the XSS vulnerability, extract the cookie from the request, and make use of it for the remainder of the attack. However, there's another more interesting and easier option to explore. Rather than stealing the cookie, we could leverage the XSS vulnerability to force our victim to execute whatever action we want within the @mail web application. In this way, we would ride the victim session, turning our XSS into a CSRF attack, also known as session riding. To automate our attack, we can use the JavaScript XHR API. This allows us to establish a bidirectional communication channel between the web application, the server, and the victim session without the victim having any knowledge of the attack. To demonstrate the session riding attack, we'll try to keep things simple and develop a JavaScript payload that will send an email to the address of our choosing from the compromised admin account. First, we need to identify the correct URL used to send an email and determine what a normal request looks like. In order to streamline the development process, we'll use the @mail web UI and admin user credentials on our Kali machine alongside our intercepting burp proxy. This will allow us to simplify our effort since we will not rely on stolen sessions. We can compose a test email and send it while capturing all generated traffic in burp. Let's log into the web application and use Burp Suite to capture the request. Our burp proxy is configured to proxy and not intercept. Let's log in first. Now that we're logged in, let's click New to compose a message. We'll send the email to our admin account. Now we can send this email and review what the post action is in our proxy. Excellent. Now that we have an example of the post request to send an email, we can use it to craft our payload. The next step is to minimize the request to reduce the complexity of creating an exploit. To find which variables to remove from the post request, we can either review the source code or find out by trial and error. We'll use Burp's repeater to resend the post request and remove parameters. After a number of attempts, we narrowed the parameter list to 3. We can send an email using the email to, email subject, and email body HTML parameters. Let's test that now. Good. There are no errors in the response. If we check our inbox, we can see that we received another email. To keep our testing environment tidy, let's empty the inbox. Another change we can try is to swap the post with a GET request. Burp makes changing the request method easy. We just right-click the request and select Change Request Method. Let's try this request and see if we can successfully send an email. Nice. We don't see any errors, and if we check our inbox, we see that we did get an email. Now that we have a more compact request, it will be easier to create our attack. After minimizing the HTTP request, we can start developing the JavaScript code that will execute this attack in the context of the admin user directly from the victim browser. First, we'll create a new JavaScript file called @mail-sendmail-xhr, which will contain the session writing payload. Let's open this file in a text editor. This code is fairly simple. The 3 variables in the minimize request are set in the beginning of the file. Next, the function sendMail sets 2 variables. The first is the URI, which is the same path we used in our minimized request. The second is the query string, which is also very much like our previous minimize request. Starting on line 10, we create an instance of the XML HTTP request object in order to craft our malicious GET request on line 11. Then, we use the object to initiate a request with a URL that includes the URI variable and our query string. If this code executes correctly, It should send an email to the attacker email address on behalf of the admin user. Most importantly, this will all be automated and done without any interaction by the logged in admin user. Notice how the JavaScript code does not use any cookies. This is because we are simulating the request forgery attack by executing the script from the browser that's already logged into the Atmail application as admin@offsec.local. Since this code executes without interaction and the HTTP session is legitimate, we should be able to use this to send our test email from one account to another. Let's use this JavaScript file in our attack. We'll clear our inbox first. And we'll again set up a simple Python web server. Let's switch to our other terminal to send our payload. In our payload, we are including the atmail sendmail xhr.js file. So let's send this off. And now let's log into the attacker mail account to check if our email was sent through the session writing attack. Check your course materials for the most current credentials. Here, we're logging in with attacker@offsec.local and the password 123456. Unfortunately, the inbox is empty. The JavaScript execution was not successful. Before debugging our failed attack, let's go back to our admin account. If we look back at our terminal, we see that the JavaScript was requested by the browser, so now we need to find out what went wrong with the code. To debug or review the JavaScript, we'll use the browser's built-in developer tools. We can toggle the developer tools by clicking the area in the lower right. Within the developer tool console, we'll select the JS tab. It seems there's an error associated with our atmail sendmail xhr.js file. The two numbers here are the line number and character position of the error. And the error is an unterminated string literal. Let's click the file name link to see its source. When we do this, we see that the line in question is highlighted for us. If we inspect the query string variable carefully, we can see that we made a mistake in our code. We have a quote to surround the email body HTML portion of the query string, but we never close it before appending the message variable. Thankfully, this is a simple fix. We'll just close the double quotes after the equal sign. Let's quickly open and fix this file now. We'll add a quote after this equal sign and save our file. We still have the malicious email in our inbox, so we should now be able to go back to the browser, click the inbox, and execute the payload. Let's see if this works. Our payload should have executed, and now we'll log into the attacker account again to see if our email was sent. Excellent. Depending on how many times you've clicked on the inbox or refreshed the admin mailbox page, you may see a few emails here. We now have a working payload that will send an email using an authenticated session without the user's knowledge. Let's take a moment here to recap what we've done. First, we sent an email to admin@offsec.local that contained a malicious payload in the date field. This pointed to a JavaScript file hosted on our attacking server. We created a JavaScript file on our attacking server that is called by the tag described in the previous step. We included code in the JavaScript file that'll send an email from admin@offsec.local to attacker@offsec.local. Next, we started a simple Python web server from the same directory where the malicious JavaScript file was located. Then, we logged into the admin account to trigger the XSS. This emulated actions on behalf of the victim user. Now that we've established how to perform actions as an authenticated user, let's look for other functionality that we can use to compromise the Atmail system. As attackers, we want to find a way to gain full control of our target, and that means compromising the entire underlying operating system. Many times, one vulnerability alone is not sufficient. In the case of AppMail, we know that we can use the XSS vulnerability to hijack the administrative session. This means that not only can we reach the authenticated part of the application code, but also the extended administrative functionalities. Crafting a malicious plugin is one possible approach, but we're going to explore application functionality, which, in our opinion, is a more interesting approach to gain remote code execution on the target system. The attack vector we'll describe is a small chain of vulnerabilities that elegantly subverts the logic of the application. In order to do this, we'll make use of two vulnerabilities. The first weakens the posture of the application via changes to the global settings, and the second makes use of this weakened posture to upload malicious PHP code. In order to develop the exploit, we will first change the global settings of the application. This is going to require administrative access. Next, we'll upload a file via an email attachment. This requires mail user access. And finally, we'll access the uploaded file so that it's executed by the server. This does not require special privileges. In order to properly identify and understand the vulnerabilities used in this section, we'll need to dive into the source code of AppMail. Since we are targeting an email application, we can assume that the email attachments will be accepted by AppMail. This means we should already have the ability to upload arbitrary files to the target server. The question is, what security mechanisms does AppMail use to prevent a user from uploading and executing malicious files? In order to understand this, let's capture a POST request when attaching a file to an email. We'll log out of the attacker account and log back into the admin email and administrative account. First, let's clean up the mailbox. Now we'll compose an email and attach a file. We'll create a file named appmail.txt in our home directory here in the terminal. Now in our inbox, we can click New Email. Next, let's click Add Attachment and select our text file. Now let's look at our proxy. We're looking for the POST request that alludes to adding an attachment. Looking through some of the POST requests, we see one that posts to a URL that includes the term Add Attachment. We can see that the attachment gets uploaded immediately, so let's try to find the source code of this function. But before doing that, let's just take a note of the POST variables used in the request, namely name and file name. In order to review the source code, we'll use the file manager to secure FTP to the AppMail server. Be sure to check your course materials for the credentials for the AppMail user. Since we saw the term add attachment in burp, in order to identify the file containing our target function, we searched for any occurrence of add attachment in the AppMail source directory. By doing this, we discovered the implementation of the attachment handling logic in the file compose-message-controller.php. Let's look at that file now. The function we're looking for is add attachment action, and that is found on line 1129. Carefully inspecting the code, we see a couple of things of interest. First, on line 1137, we see that the file name original variable is set using the user-controlled file name we noted in the previously examined POST request. On lines 1138 and 1139, we see that the AppMail developers were mindful of file name manipulation. On line 1138, dots or forward slashes at the beginning of the file name are replaced. On line 1139, after the beginning characters have been replaced, the string replace function removes all combination of two dots and a forward slash. This prevents uploading of files like htaccess and deters directory traversal attacks. On line 1141, a new variable called filenamefs is created. This partially consists of the filename original variable. On line 1143, the file name fsabs variable is set. This variable is made up of the variable approot, the value returned by the user's getTMP folder function call, and the file name fs variable that was set on line 1141. Let's investigate the function users_getTMP folder. We can find this function in the users.php file. The getTMP folder function can be found on line 120. Although a bit intimidating at first glance, this function is fairly easy to follow. We'll start by looking at the constant approot, as it is used in this file many times. We see one example on line 143, however, we're not as interested in this specific instance. This constant is initially defined during installation in the file serverinstall.php. This file is located in the user local @mail directory. Let's open it now. On line 21, the approot constant is defined. This constant is set to the current directory, which is indicated by the dirname function, calling the magic constant file. Next, we see that the current file's directory is appended with the predefined directory separator constant. The next append is the string webmail, which is then terminated by another directory separator. The end result is that the approot is equal to the user local @mail webmail directory path. Now that we know the contents of the approot constant, we can return our focus to the users.php file. On line 130 in users.php, the directory variable tempdir is obtained from the global configuration variable temp folder base name. A quick search through the @mail PHP files revealed that the temp folder base name value is stored in the database, and its default value is set to tmp/ during installation. The installation script that sets this value in the database is @mail6 defaultconfig.sql. This file is located in the @mail install directory, so let's open it in our text editor. In this file, we find that a number of configuration settings are inserted into the database. If we search for temp folder base name, we find that it's set with the value tmp followed by a /. Now that we know both the approot constant and the temp folder base name variable values, we can go back to users.php. On line 148, we find that the safe user variable is created using the username of the user triggering the execution of this code. In other words, the @mail username trying to send an attachment. Before being used, the username is simplified through the use of the simplify string function, which just removes special characters from the string content. On line 150 and 151, the first and second characters of the username are extracted and later concatenated into a folder path. Farther down, we find that if the folders do not exist, the code creates them. This logic can be seen on lines 166, 170, 175, 179, 184, and 188. Thinking back to the add attachment action function, and based on what we've learned from the getTemp folder function, we can conclude that the final upload path for any attachments uploaded by the admin user is user local @mail webmail tmp ad admin offsec local. This path is located within the web root, and if any PHP files are uploaded here, we can potentially gain remote code execution by accessing them. However, we still have a problem we need to overcome. If we look at the file system of our @mail server, we discover that the parent upload directory, user local @mail webmail temp, contains an htaccess file. Since the file we're looking for is hidden, we can hit Ctrl-H on the keyboard to display it. Now we can inspect the htaccess file in a text editor. As it stands now, the htaccess configuration will deny all HTTP requests for any file within the current directory and subdirectories. Okay, let's recap. We can potentially upload any PHP file of our choice by crafting a session writing attack. We could do this by forcing the victim to send an email containing an attachment processed by the add attachment action function. The temporary folder path where the attachment would be stored is predictable and within the application web root, as we saw from the getTemp folder implementation. However, the htaccess file stored in the temp directory would block the requests to our malicious uploaded PHP file. So the next question is, how are we going to defeat the htaccess file protection? In the previous section, we learned that the temp folder base name is set in the database through the @mail6 default config script. By looking at the other content in this file, we realize that at least some of the variables set during the installation can be changed through the administrative web interface settings. Let's take a look at that in the application. Notice that here we are logging into the administrative interface and not the webmail portion of the application. The area where we can update configuration settings is found in the web user interface by clicking Settings. We do not see a way to update the temporary directory path directly, but the existence of this update mechanism suggests that it may be possible to make a change to temp folder base name with a specially crafted request. Why is this important? Let's take a look at the file system. The default value of the temp folder base name setting is temp/. When concatenated with the web root, it is user local @mail webmail temp. In the previous section, we described how this setting is used as part of the path destination for a file upload. If we update the temp folder base name setting to an empty string, we'll effectively move the upload parent folder up one level to the webmail directory. Even though the difference is very subtle, we can validate that the webmail directory does not have an htaccess file. Here, we can see that there is no htaccess file. In other words, if we're able to change the global setting as described, we can avoid the restrictions imposed by the htaccess file located in the original temp directory. Let's proceed by intercepting the post request issued while saving the global settings from the UI. This will help us find any possible flaws in the code logic. Now, let's find that action in our proxy. Here we can see that the post URL ends with global save. We found the term function global save in the settings controller.php file after searching the code base. Let's take a look at that file. We want to find the term function global save. Let's see how the changes to the global settings are implemented. For us, the most important items in this function are located on lines 187 to 188 and 213. As we know, the global settings are saved in a database, which implies that any changes to those settings through the UI also need to be saved to the same database. This code looks for a request parameter called SQL pass in the fields array, but if it is not set, or is set to the MD5 hash of the string unchanged, it retrieves the database password for us on line 188. Retrieving the password allows us to establish a successful connection to the database at lines 202 to 203. And finally, on line 213, we find a call to the save function in the config class. We can find the config class implemented in the file config.php. Again, we'll use the file manager, and we'll navigate to the webmail application models directory. Let's open config.php in our text editor. Here we can see the config class is defined, and the first function is the save function we're looking for. We can see that it expects two parameters, section node and new config. Remember that in settingscontroller.php, we saw that the save function was called by passing global as section node and the fields array coming from the HTTP post request as new config. Again, we're trying to determine if we can update the temp folder base name setting, so let's analyze this function and see if that's possible. For this, we'll assume that the new config request array can also store a modified temp folder base name value. A little farther in the code, we find that the parameters submitted in the post request and stored in the array new config are broken up into key and value pairs. The subsequent for loop on line 36 looks through each configuration variable name as retrieved from the database and compares it with the keys of the new config request array. If the variable name matches one of the array keys, the code will enter a different branch based on the type of the specific configuration variable that's being updated. In our case, we're interested in updating the temp folder base name setting, which is neither an array nor a Boolean type value. Because of this, we'll enter the else branch starting on line 74, where finally the configuration setting in the database is updated to the request value we control without any additional checks. In other words, the @mail developers failed to account for in-transit modification of legitimate requests and assumed that only the intended subset of global settings that are exposed through the web UI could be updated. This means we can take advantage of this oversight and update a configuration that was not intended. Let's go back to our proxy where we have the save settings post request. Send this request to the repeater and see if we can manipulate it to change our temp folder base name. We'll also SSH to the @mail server to make sure that our proof of concept post request actually changes the temp folder base name setting in the database. We'll launch the MySQL client, connect to the @mail database, and check the temp folder base name settings. Again, be sure to check your course materials for the SSH and MySQL passwords for your lab environment. Let's verify the value for the temp folder base name setting. We see that the value is temp/. We want to change this because it contains a restrictive htaccess file. Let's go back to our post request. And first, we'll send this request without any modification. Good. Now that we have an example of a successful submission, we can try to minimize our request as we did previously by removing some of the parameters. After some trial and error, we determined that the only items required in the post are the save parameter and the SQL user entry of the fields array. Now let's add the temp folder base name to this request and see if we can update its value in the database. Okay, we'll click Go and see if this is successful. The request looks successful, so let's switch to the terminal and have a look at the database. Running the same query, we see that the temp folder base name value is now empty. We've successfully updated a global setting in the application, which should now allow us to upload a file in an area that we can access. Now that we've changed the appropriate global setting in the admin interface, we can upload content through the webmail interface and then access it using a URI that we know. Let's log into the web interface, compose an email, and capture the add attachment post request. Now we'll create a new email and add an attachment. Let's go back to our proxy and check the history. This is the post that uploads the attachment. Let's send it to the repeater tab, change the file name, and also the content of the uploaded file. We can include any PHP code, but for now we'll use the PHP info function. Let's submit this request and see if we can locate the file on the target file system. Recalling our analysis of the upload function, there were 3 directories based on the username. The first was the first letter of the username, the second was the second letter of the username, and the last was the full username or email address minus special characters. Specifically, we should have a file in the directory ad admin offsec local. Let's try that directory and see if we get a response. Excellent. A forbidden response is good. This means the directories exist. Now we need to figure out our uploaded file's name. Let's switch back to our burp proxy for a moment. In the response to our post, we can see a few interesting things. The response from the server appears to display what might be an uploaded file name. Let's add this file name to our browser and submit the request. Excellent. We found the file. Now we know how to use an existing session to upload PHP files. Let's go back to our repeater and see if we can again minimize the request. The first thing to look at is the long file name we have. It begins with text plain, and after reviewing our request, we find that the file upload displays a content type of text plain. Let's see if we can submit an empty content type. Interesting. If we submit an empty content type, that portion of the file name is omitted. We also see the file name starts with a dash. However, there is another variable portion of the file name. Again, looking back at our request, we can see that the post was made to a path ending with a specific value, which is then reused as a portion of the file name. Let's try the same technique and remove the end of this path and resubmit our request. Great, we were able to reduce the file name to something much smaller and predictable. We're now ready to put the pieces together and weaponize this exploit. Let's use our original cross-site scripting vulnerability to change this setting. Since we need an account with access to the administration panel, we'll again target the admin user. The condition we need for this attack to work is for the admin user to be logged into both the webmail interface and the administrative interface. Let's change the temp folder base name setting back to tmp/ and remove the new directories we created as a cleanup step. Then we'll redo this attack via malicious JavaScript. We'll add the temp to the temp folder base name and click Go. Now we'll double check that the temp folder base name setting has been restored in the database. Great. Now we just need to remove the new directories we created. Good. Now that we're back to our original application state, let's change our malicious JavaScript. We'll exit our session from @mail and edit the @mail sendmail xhr file. We're going to make changes to this file so that we modify the settings in the administrative interface and upload a file. The first function we'll create is pwn setting temp folder base name. This function updates the global settings and sets the temp folder base name to blank like we did earlier. Next, we need to add a function for our file upload after we've changed the temp folder base name setting. This function is a little more complicated. On line 14, we set the content of our PHP file. This content is a reverse shell that takes both an IP address and port number as arguments. Next, we set the file's size and the boundary, which is required in our file upload. Next, we set the upload URI. On line 18, we create an instance of the XML HTTP request. And then on line 19, we generate a post request with the appropriate URI. On line 20, we set the content type header, which sets the boundary for file upload. On lines 22 through 26, we define the body variable, which is used to set the attributes and content of the uploaded file. Lastly, we send the post request on line 28. Now that we've set up each function, we can call them to perform our actions. One thing to notice on lines 32 and 33 is that we call the functions in different ways. On line 32, the pwn setting temp folder base name is a standard JavaScript function call. However, while testing this exploit, we notice that calling upload all the things immediately after the setting change did not allow enough time for the setting change to take effect. Therefore, we call upload all the things using the set timeout function, which delays the request by 1000 milliseconds, or 1 second. Now that we have an updated JavaScript file, let's save it and see if we can combine our settings change and file upload. We'll launch our attack from another terminal. Now let's check our admin mailbox. Great. Now if all went well, we should be able to find our file with a browser. Let's set up a netcat listener on port 4444 and see if we can catch a shell. Also remember that our PHP reverse shell needs to be called passing the IP address and port parameters. First, let's go to the browser and verify that our PHP file was uploaded. Okay, this is a good sign. We did not receive a 404. Now let's add our parameters and check our netcat listener. Excellent. We now have a reverse shell. In this module, we first discovered and then later exploited an XSS vulnerability in the @mail server. We showed how this vulnerability is triggered when a user views their inbox. Next, we combined the XSS vulnerability with a post-authenticated payload via session writing to send an email on behalf of the administrator to any user, essentially spoofing the administrator. Finally, we walked through a file upload vulnerability and built an end-to-end exploit combining all the previous steps. This exploit resulted in remote code execution, which compromised the underlying server. A-Tutor authentication bypass and remote code execution. In this module, we'll cover the analysis and exploitation of multiple vulnerabilities in version 2.2.1 of the A-Tutor Learning Management System. We chose this application because A-Tutor has a large user base and is open source, which gives us the possibility to adopt a white box approach. The first vulnerability we'll investigate is a SQL injection that can be used to disclose sensitive information from the A-Tutor database. Once disclosed, this information can be used to subvert the authentication mechanism and give us privileged application access, which we'll leverage to obtain remote code execution. As a first step, we'll enable database logging to better debug the application during the vulnerability discovery process. To help with our analysis, we'll SSH to the A-Tutor host and also enable the PHP display errors directive, which will provide us with more verbose output while testing. To do that, we'll edit php.ini on the A-Tutor server. Let's find the directive display errors with the Ctrl-W shortcut. We'll set this directive by replacing off with on. Great. Now let's save and close this file. We also need to restart Apache for the new configuration setting to take effect. Next, we'll configure MySQL to enable database logging by editing the my.conf file. Let's search for the term general underscore and remove the comment characters from the general log file and general log lines. That's all we need, so let's save and close this file. After modifying the configuration file, we need to restart the MySQL server in order for the changes to take effect, so let's do that now. We can use the tail command to inspect the MySQL log file and see all queries being executed by the web application as they happen. We'll run the tail command with the -f option to display new entries as they're added. To test the logging, we can simply browse the A-Tutor web application. We'll quickly navigate to the search page to make sure we're seeing activity in our log file. Great, it looks like we're logging all of our SQL queries. Now that we have MySQL logging and PHP errors set to on, we're ready to start our white box vulnerability discovery process. Let's first look around and get a feel for the application. When we performed some preliminary profiling of this application, we found that all publicly accessible ATutor web pages were easy to identify. All pages that do not require authentication contain a line setting the user location to public. As an example, let's check the search.php file that we've browsed in our previous test. Here we can see that the variable user location is set to public. Unauthenticated portions of application code usually take priority as they're typically accessible to anyone, making them easier to exploit. In this module, a vulnerability in the unauthenticated portion of the code will allow us to gain the initial foothold. We'll then escalate our privileges by exploiting vulnerabilities in the authenticated section of the application. Let's enumerate all the pages that don't require authentication with a regular expression grep search. In this command, the -r flag means that grep will look recursively, and the -e flag means that grep will use a regular expression that looks for the user location variable set to public. Lastly, we're using the color flag to help make the results more readable. Our search returns a number of files that are accessible without authentication. In these files, we began searching for SQL injection opportunities, and after some time, we discovered a potentially interesting candidate. Let's look at the code found in indexpublic.php in the social subdirectory. In this file, the user location variable is set to public, and the rest of the file does not indicate that authentication is required. Let's take a look at this file in our browser. Great, so we can access this page without authentication. Let's look back at the source code a bit more. Here, there are checks to see if the p and rand key variables are set. These are not really interesting, but if we scroll down further, we can see that if the getQ variable is set, the value that it holds is sanitized using the add slashes function on line 39. Then the query is passed on to the search friends function on line 42. We pay close attention to function and variable names like query or search, since they're directly related to user-controlled input, and their sanitization methods need to be verified. Many times, following a code flow like this will lead to a dead end of well-sanitized data. But at the very least, this exercise will help you understand the protections used in the application. Let's follow this function call and see how ATutor handles user-controlled input. First, we'll find where search friends is defined. We'll go back and search the files in the web root and grep for the file that declares the search friends function. Great, we found a file in the lib directory of the social module called friends.inc.php. Let's take a look at this file to see how search friends is implemented. We'll search for search friends. Great, we found the search friends function declaration on line 260. At the very beginning of the function, we find add slashes again, indicating that we'll likely have to deal with some sort of sanitization. On line 271, we see the sanitization attempt happening as expected. Then on line 272, our user-controlled name variable is exploded into an array called subnames, using a space as the separator. After the array is created, there is a for each loop that iterates over each portion of that array. Within the for each loop, we also see that the piece variable, each item in our array, is added to the match piece variable. This variable is then used as the like operator in the partial SQL statement on line 289 in the query variable. Further down in the script, we see that line 342 is where we append our query variable to the SQL variable. That string is then passed to the query_db function on line 347, which executes the query against the database. At this point in our analysis, recall that we have seen at least 2 attempts to sanitize user-controlled input. In theory, this potential vulnerability seems well defended thanks to add slashes, despite the fact that user-controlled input is part of the SQL query. However, if we send a properly crafted GET request with a payload containing a single quote, we observe something interesting. We can also achieve the same result by using the Python script found in your course materials. Let's take a look at that script. The script starts by importing the necessary modules for the functionality we intend to implement. Next, the search friends SQLi function is defined. This function takes an IP address and a query injection string and submits an HTTP request, then parses the response. Lastly, the main function is defined, where we print the script usage if the command line arguments are not supplied correctly. Let's use this script to make a request similar to the single quote request we made earlier. We are passing 2 arguments to this script, the atutor hostname and the characters to inject into the queue parameter. Let's submit this request and see if we obtain the same error. Great, our Python script is working. Remember that we're only seeing these errors because we changed the PHP display errors setting, which isn't typical in a production environment. Let's look at that error in more detail. We're already familiar with the file friends.inc.php, but let's take another look to check what is causing the error on line 350. Line 350 uses the rows members variable, which should be populated with the results of the query executed on line 347. This indicates that the query may be broken. With MySQL query logging enabled, we can check out the log file. Let's go back to our SSH session and take a look. Here, we can see that our payload of 4 capital A's, along with the single quote, is being injected into the final SQL query. A single quote making it through to the query is a success for us and validates that this is a SQL injection. Next, let's send some other test payloads to get a better idea of how we might use this SQL injection. We also see that by sending a single parameter, we have 4 injection points. We'll need to keep this in mind as we craft our exploit. We'll send the same payload as before, but with an additional single quote. This output is a good sign and could mean that we have successfully closed our previously open single quote and have executed a well-formed SQL query. Let's validate this by checking the MySQL log. And we'll look at the end of the MySQL log again using tail. Excellent. We do not see any errors. This confirms that the SQL query is well formed. If you're familiar with SQL injections using union queries, you might think this is a perfect opportunity to use them to expose arbitrary data from the database. However, a union query is not helpful here. Let's find out why. If we look at the code in indexpublic.php and navigate to line 48, we can see that the results of the vulnerable query are not actually displayed to the user. Instead, the query result set is used in a for each loop that uses the retrieved member ID value and passes it on to the print social name function. The results of this function call are then displayed to the end user using the PHP echo function. In other words, the results of the payload we inject are not directly reflected back to us, so a traditional union query will not be helpful here. We can verify this by continuing to follow this code execution path. The print social name function includes a call to the getDisplayName function, which is defined in vital.funcs.inc.php. We can verify this by continuing to follow this code execution path. The print social name function includes a call to the getDisplayName function, which is defined in vital.funcs.inc.php. Let's take a look at this function. We'll navigate to the getDisplayName function and jump to line 297, which puts the function declaration at the top of our editor. On line 304, the final query is created and the results are returned back. This logic effectively prevents us from using any union query in the original vulnerable query and turns this SQL injection into a blind injection. Unlike very basic SQL injection vulnerabilities that display data, blind SQL injections force us to infer the data we're looking for because it's never returned in the result set of the original query. Let's take a moment to talk about traditional blind SQL injections. In a blind SQL injection attack, no data is sent back from the web application, so we can't see the result of an attack in band. But we can ask a series of Boolean or time-based yes and no questions to piece together the results of the attack. In Boolean-based blind injections, we send an SQL query to the database, which forces the web application to return a different result depending on whether the query evaluates to true or false. In time-based blind injections, our ability to infer information is even more limited because a vulnerable application does not display any differences in the content based on our injected true or false queries. In these cases, the only way to infer any information is to inject SQL commands that delay the query execution by using database-native functions like MySQL's sleep function. Let's figure out which type of blind injection we're facing here. First, we'll open our browser and navigate to the vulnerable application, supplying the prefix of a known and valid user to the queue parameter. Our ATutor installation already has an offensive security user, so we can use the prefix OFF. Excellent. In this web response, the application displays some data within the HTML page. Now, recall that earlier we executed a valid query using our script by injecting 2 single quotes. Because this payload created a properly formed query, we didn't observe any errors. Let's perform the same query from the browser. This time, the application does not return any suggested results. This validates that we can control the observable output, which means that we're dealing with a Boolean-based blind injection. Now, let's dig a bit deeper. During our source code analysis, we identified a few spots where the ATutor developers used a function called add slashes against user input from the queue get parameter. A quick look at the PHP documentation verifies that this function should indeed escape our single quote payload, yet it didn't. Let's investigate. If we look closely, we see that the called function name is stored in a variable called add slashes. This is not the native PHP add slashes function. Let's egrep for the add slashes variable. It looks like it's defined in the MySQL connect.inc.php file. Let's take a look. Now, let's find the add slashes definition. There's a check for the magic quotes setting on line 92. If magic quotes are on, then add slashes is defined as my add null slashes on line 93. On our vulnerable system, we can test this conditional statement and see if it would be taken. Let's create a quick PHP file that will give us the status of the getMagicQuotes function. Now, let's use curl to get the response from our magic.php file. We can see that this check returns false. This is expected because magic quotes have been deprecated since PHP version 5.4.0, and our installed version is newer. Let's take a look at our current PHP version to confirm this. We'll use the same magic.php file and paste in the directive to echo the current PHP version. Just as expected, we're using a version much newer than 5.4, and therefore magic quotes checks will return false. Let's clean up before carrying on. Now we'll return to mysql connect.inc.php and resume our analysis. Looking at the code on line 92, we know that the if condition will fail. This means we'll move to the else portion of the conditional branch every time. Next, line 96 checks whether the global variable mysqli enable is defined. If it is, then add slashes becomes the trim function. How can we find out if mysqli enabled is true? Let's figure out where it's defined. We'll make an assumption that it would be defined with the define function and search the code using the following. Excellent. We can see that there are two files where mysqli enabled is set, and we'll choose the one that is not in the installer subdirectory. Let's take a quick look. When we open the file, we see that mysqli enabled will be defined if the function mysqli connect exists. Since our atutor installation runs on PHP 5.6, the mysqli connect function must exist, as it is present by default since PHP version 5. This means that we can be certain that mysqli enabled will be set to 1. Let's sum up our analysis by going back to mysql connect.inc.php and navigate to where add slashes is defined on line 93. We verified that magic quotes return 0, and this takes us to the else statement. Then we know that mysqli enabled is defined, and therefore the add slashes variable will be set to the trim function. This means that in our case, add slashes will not sanitize any user input. Nice. This is a great find, but we need to take this further to get to full SQL injection. Let's take a look at the next hurdle. Atutor defines and implements a function called Security-AWAE, whose purpose is to enable the use of parameterized queries. The Security-AWAE function is called anytime there is an SQL query to be executed, and it is defined in the MySQL connect script. On line 119, we find that when the Security-AWAE function is used correctly, the known and controlled parts of any given query are passed as the first parameter. The user-controlled values are passed in an array as a second parameter, which are then properly sanitized and used to construct the complete query. The sanitization happens in the create_SQL function, which we see used on line 123. This create_SQL function is also defined in the mysql connect.inc.php file, so let's search for its definition. Here on line 182, we can see that the create_SQL function is defined, and by default, the sanitize value is set to true. Now, let's go back to the file manager and open the file with the search friends function to better understand how the parameters are processed in our specific case. And here we'll open friends.inc.php. Now let's look at the MySQL connect.inc.php file and find the create SQL function on line 182. As we've already seen, the developers intended that the first argument to create SQL is the parameterized string, and the second are the user-controlled parameters. However, if we look back at friends.inc.php in our other tab, and we jump down to line 347, we can see that search friends assigns a value to row members by calling query_db and passing the SQL variable and an empty array. This is significant because it means that the entire query is passed to the query_db function in the first parameter. Switching back to MySQL Connect, we can see that only the items in the array are sanitized. Specifically, the for each loop on line 186 iterates through every item in the params array, and each string value is sanitized using the real escape string function on line 189. Effectively, this means that the query string is built by concatenating the unsanitized string, which is then passed to the query_db function. This avoids sanitization because the user-controlled parameters were not passed in the array. This mistake, combined with the add slashes definition described in the previous section, contribute to the SQL injection vulnerability we discovered. The incorrect use of the query_db function is an example of a software development mistake that we've encountered numerous times when auditing web applications. This type of mistake highlights what can go wrong even when secure functionality has been built within an application. In this instance, the function was built securely, but was not used correctly. Now that we have a complete understanding of this vulnerability, let's see how we can exploit it. Before attempting to extract data from the database, we must keep in mind that our payloads cannot contain any spaces, since they're used as delimiters in the query construction process. Let's take a look at that code again in the file friends.inc.php. On line 272, we see that the name variable is split using the space character as a delimiter. Since this is an ATutor-related constraint and not something inherent to MySQL, we can replace spaces with anything that constitutes a valid space substitute in MySQL syntax. Let's switch back to the ATutor server and perform some sample queries to figure out how to avoid spaces. Let's log into the MySQL database. Be sure to check your course materials for the current MySQL root password. In our case, the password is Tor. We need a valid space character substitute for MySQL, and as it turns out, we can use inline comments in MySQL as a valid space. For example, the following SQL query is in fact completely valid in MySQL. Inline comments work perfectly. Now that we have a method of successfully bypassing spaces, we can work on crafting the Boolean queries to use in our exploit. Aware of the restrictions in place, our first goal is to create a very simple dummy true-false injection subquery. This is an important step which establishes a baseline for how the injected true and false subqueries will influence the HTTP responses. We will expand this later on and ask the database arbitrary questions by replacing the dummy true-false subqueries with more complex Boolean subqueries. Remember that we'll only be able to infer the answers to our questions by examining the differences in the HTTP responses. In the initial vulnerability discovery, when we sent 4 capital A's and a single quote, we found ourselves able to inject into a query that looked like this. Now we need to insert an injection that uses space character substitutes and will let us infer answers. Here are the true-false subquery payloads we can use to achieve our goal. Let's quickly explain these payloads. As we did previously, we start with 4 capital A's. Then we terminate the like field with a single quote. Next, we close the parenthesis that starts the where condition. We insert comments as alternative spaces surrounding an or. Then we initiate a subquery that returns the number 1, which is compared to either a 1 or a 0. The payload ends with a pound sign, which MySQL interprets as the beginning of a comment. This effectively makes the rest of the query a comment. We display the pound sign here as a URL encoded value of %23. Before injecting our sample payload into the web application, let's see what our payload looks like in a MySQL shell. First, we'll select the ATutor database. Then, we'll recreate the full query injecting our first payload. For convenience, we've also changed the select star syntax from the original query to select count star. This simply changes how the result output is presented, displaying the number of rows returned by the attack rather than the content. Okay, let's execute this query. You'll notice that we have to hit enter and add a semicolon afterwards. This is the result of the first statement semicolon terminator being commented out by our injected end-of-line comment character. Now let's submit the false version of our payload and see the difference. From the output of each query, we can see that the true-false example subqueries control the number of results that are returned from the vulnerable query. So far, so good. Finally, let's quickly check our database log file. We can see that the injected queries are truncated. This demonstrates that we're able to use a comment to terminate the query and that our injection string does not have to satisfy all 4 injection points. Now, let's trigger our vulnerability using the true statement and our proof of concept script. This will help us verify that everything's still going according to plan. This time, we'll run our script with the true payload. While it may seem obvious that the subquery select1 equals 1 will always be true, we must remember that we're verifying that the complete query and all its subqueries are well-formed and will not cause any database errors. We also want to control whether or not the database returns a result set. We can accomplish this by changing the subquery comparison value from 1 to 0. Let's take a look at the response to a comparison of 0. The false example. Looking at each of these responses, we see that when we inject a payload that makes the vulnerable query evaluate to false, the response is basically empty and our content length is 20. However, if we inject a payload that forces the vulnerable query to evaluate true, we receive a response body and the content length is 180, much larger than 20. This means we can use the content length header and its value as our true or false indicator. The updated proof of concept script in your course material includes this functionality. Let's briefly review the contents of this script. On line 4, we define the search friends SQLi function. This function takes 3 arguments: the IP address, the injection string, and the query type. The IP address is the vulnerable target. The injection string is like our example, true and false payloads, and the query type is true or false. The function makes a request and will return true if the query type and content length conditions are satisfied. Otherwise, it will return false. Next is the main function that runs when the script is executed. It first checks to make sure the correct number of arguments are passed. Then it sets the IP variable to the IP address or hostname passed as a command line argument. The next 2 strings are predefined payloads to inject into our vulnerable SQL statement, forcing the query to return true or false. Lastly, both the true and false payloads are sent, and if each of them return true, our print statement is echoed out to the terminal. Let's close the text editor and run this script against our vulnerable ATutor server. After running the proof of concept script, we confirm that both the true and false statements are working as intended. Now, let's continue to craft our payload and attempt to infer and extract valid data from the database. We finally reached the point at which we can develop a more complex query in order to exfiltrate valuable data from the database. Our first goal will be to extract the database version. Let's open up a MySQL prompt on the ATutor server. We'll craft a query to display the MySQL version using substitutes for space characters. Because we have a blind SQL injection, we have to resort to a byte-by-byte approach, since we cannot retrieve a full response from the query. Therefore, we need to come up with a Boolean MySQL version subquery that will replace the true-false dummy examples used in the previous section. Let's compare the first character of the version string to determine if the major revision is a 4 or a 5. We can start with a query that only shows the first character of the version. Great, we've extracted the first character of the version, which is 5. Here, we are relying on the substring function, which returns any number of characters we choose, starting from any position in the target string. In its current state, this query will not work for us because we cannot read responses. We need to know if our guess of a 4 or a 5 is true or false. We can accomplish this by making a comparison. First, let's test if the response is a 4. Excellent. The result of 0 tells us that the first character in the version string is not a 4. Now, let's test a 5. Perfect. Our test of the first character in the version string being a 5 returned true. At this point, it's worth mentioning that it's good practice to convert the resultant character to its numeric ASCII value and then perform the comparison. The main reason for doing this is to avoid any potential payload restrictions. Special characters like quotes or others in the injection string can potentially damage our query. While our only restriction in this vulnerability is the space character, using the ASCII value is a practice you should implement to prevent issues in your exploits. In the case of MySQL, the relevant function to perform this conversion is the ASCII function. Let's add that function to our existing queries. First, we'll try ASCII 52, which is equal to 4. That returns false, so now we'll use 53, which is equal to 5. Great. Since the ASCII version of 5 is equal to 53, the query returns true. Next, let's use our latest queries to craft true and false payloads. Our payloads should look like the following. If we test these in a browser, we should see either an empty response for false and some content for true. Let's use our first proof of concept script to test these payloads. Excellent. We can see that testing for the number 4, ASCII 52, returns false, and testing for the number 5, ASCII 53, returns true. We finally reached the point where we can develop a script to automate the data retrieval from the MySQL database using the SQL injection vulnerability we investigated in this module and the MySQL version Boolean subqueries we just manually tested. We just need to manipulate the substring function in our subqueries and loop over every single character of the version result string, comparing it with every possible character in the ASCII printable set, which are numbers 32 through 126. Let's briefly review our next proof of concept script. This script is very similar to our first one, so we'll only highlight the major differences. The first is that in our search friends SQLi function, we start with a for loop. This for loop iterates over the numbers 32 to 126, which make up the ASCII printable character range. At the end of line 7, we see that the injection string is used in the URL. Notice that the char placeholder is substituted with the string representation of the numerical value held by the variable j. Then on lines 10 and 11, if the content length is longer than 20, the function returns the ASCII value. Next on line 26, we have a loop for the length of the version string that iterates over the range from 1 to 20. In each loop iteration, the injection string changes the starting position of the substring function, and then the next line calls the search friends SQLI function. Lastly, as each character is enumerated, it's printed to standard output and then the script is done. Let's run this script against our ATutor host. Nice. Our final proof of concept script has successfully extracted the database version. Now that we can extract basic information from the database, let's craft a more sophisticated attack. So far, we've developed a way to retrieve arbitrary information from the vulnerable ATutor database. And while that's a good first step, we need to see how we can use that information. An obvious choice would be to retrieve user credentials, but considering that modern applications rarely store plain text credentials, we would likely only be able to retrieve password hashes. This is the case with ATutor. So even with password hashes in hand, we would still need to leverage a brute force attack in an attempt to retrieve clear text passwords. Since this isn't a password cracking course, we'll investigate the ATutor login implementation for any weaknesses. Let's first open Burp Suite and capture a valid login. We'll select Temporary Project, and we'll choose the Burp defaults. We'll also open a browser that's configured to use the Burp proxy running on port 8080. Now we can navigate to the ATutor application and switch focus to the Burp Suite and navigate to the Proxy tab. On the Intercept tab, we'll make sure that Intercept is off and navigate back to our browser. Now let's capture a valid login using Burp proxy so that we have a good starting point for our analysis. We'll log in using the teacher account. In our case, the username is teacher and the password is teacher123. Now that we're logged in, let's go back to Burp and take a look in our proxy history for the login request. Here it is. Notice that one of the parameters passed to the server for authentication is form password hidden, which appears to hold a password hash. We do not see our plain text password anywhere in this post request. Let's switch back to the ATutor server and validate that the password hash we see in the post is the same as the one stored in the database. We'll select the login and password from the AT members table. The values we see in the database and our login post request do not match. This means that the password hash submitted in form password hidden is not directly used to log in a user, but manipulated by the application. In order to fully understand the authentication process, we need to start analyzing it from the login page. Let's start reviewing the code in the login.php script and navigate to the ATutor web root. Let's open this in a text editor. Looking at lines 15 to 18, we see that the login page is public and that it includes two files, vitals.inc.php and loginfunctions.inc.php. The most important piece here is to know that the login page uses functions from loginfunctions.inc.php. Let's take a look at that file. We can find it in the include directory. And here we'll open loginfunctions.inc.php. The first interesting find begins on line 23. If the login post request contains a variable named token, we can see that the session variable token is set with its value. Session tokens are always interesting items to keep track of, as they can be used in unexpected ways. We'll make a note of this and move on for the moment. The next chunk of code we want to focus on begins on line 60. The if statement on line 60 starts by checking if cookie login and cookie pass are set. We did not see any cookie set in the intercepted request or in the code so far, so we'll assume these values are not set, which brings us to the else if on line 66. In this branch, if the post variable submit is set, then the end user can set the this password and this login variables. We definitely need to make a note of this. We also see that on lines 91 and 92, the add slashes variable is used to call a function that, thanks to our code review, we determined will be trim. These are other good notes to keep in mind as we move forward. Let's move on to the next interesting chunk. On line 111, there's a cookie check. We are not using cookies in our scenario, so we'll move to the else branch on line 117. In this branch, the row variable is set to the result of the query-DB function, which contains the authentication query. The first thing we notice is that the query-DB function is used correctly this time. Remember that the query-DB function takes 3 arguments. The first is a string with placeholders for parameters. The second is an array of the parameters to be used in the query. And the third is a true or false variable, letting the function know whether or not to sanitize. Since the query-DB function is used correctly, we won't find a SQL injection here. If we manually substitute the array parameter values into the query, we can start to see the logic of how the post request is processed. Let's copy row 118 into a new text document and make some quick replacements to fully understand what's happening. First, let's isolate the query and the parameters. Now, let's remove everything that is not a query or the array. We'll also format this a bit to get a better idea of how it fits together. For our purposes here, we no longer need the select portion, so we can remove that. Now let's replace the array pieces in the from and where portions of the query at each %sign. What's important here is the section after the and. If we isolate the password comparison, we'll notice that the password from the database and the session token are concatenated. Once they're concatenated, we see that the combination is hashed using SHA-1. This SHA-1 hash is compared to the this password variable, which is a request parameter under our control. In other words, we can control 2 out of the 3 components in this comparison, the session token and the this password variable. The only portion of this comparison we do not control is the password retrieved from the database. We know we can retrieve the password value from the database using our SQL injection from the previous section. Let's look back at the code and see what happens if we can manipulate this query to return a result. On line 122, a complicated if-else statement begins. The area we're concerned with begins in the else-if branch on line 128. If the query returns a result set, then the row variable is greater than 0. The session variables are set, and the user is logged in. At this point, we know that we can control all 3 critical values used in the authentication query. Our next step is to rework our existing extraction script to retrieve a password hash of a user. You'll find a script template in the course materials, which we'll review and update now. The search friends SQLI function is the same as in our previous proof of concept script. As a quick reminder, this function makes a request and determines if the query returned true or false based on the content length returned from the application. On line 15, we see a new function named inject. This function takes 3 arguments, R, INJ, and IP. The R argument establishes the range or the length of the string we are trying to exfiltrate. The INJ argument is the query or subquery we'll use to extract data. And lastly, the IP argument is the target. This parameter is passed so that the inject function can correctly call the search friends SQLI function. The inject function then iterates over the range provided to extract each character of a string of the query result. The injection string should look familiar, as it's the template we used when extracting the database version. Next, the inject function calls search friends SQLI using the injection payload and the target IP address. On line 20, an if-else statement will capture and print the character values that return true or end the loop. Next, in the main function, we see that lines 39 and 42 need to be fixed by entering the appropriate queries to extract the username and password. Let's focus on these queries to get our script working correctly. Our vulnerable ATutor server has only one user in the AT members table. However, we should consider a scenario where there are multiple users. In MySQL, we know that we can limit a query to return one entry by using the limit clause. Let's go back to our MySQL session on the ATutor server. We'll start with our username query. Let's see the contents of the AT members table. Here we can see that we have one row of data and a lot of columns. Notice that the status for the teacher user is equal to 3. Since we want to craft a query for just the username, let's try that. This query would work for us, but remember that this is an example server and a real ATutor server would have multiple users. Furthermore, we want to target a privileged account and not just a student account. To do that, we'll tweak this query to return one teacher-level account. Excellent. But is this query ready for our script? Remember, we can't use spaces, so we'll need an alternative. Let's update our query with comments instead of spaces and test it. Perfect. Let's paste this query into our script. Next, we need to grab the password hash of this user. Let's reuse the query and change login to password. This query will work for us since we only have one user in the database, but let's tweak this a little to make 100% sure that we're obtaining the password hash of the correct user. We can do this by adding a where clause and using the username we obtained in line 40 as part of the query. Here, we'll use the username from the first query to make sure that the password hash is the correct one. Let's save this script and try it out. Excellent. Now that we have a username and a password hash, let's continue to take advantage of the authentication mechanism implemented in ATutor. In the previous section, we discovered that the ATutor authentication mechanism relies on a token and a password hash that's stored in the database. If we can discover the password hash, the entire authentication mechanism falls apart. In fact, since the token is under our control, it turns out that the form password hidden value can be trivially calculated. Let's take a look at how this value is calculated within the client-side JavaScript deployed in the ATutor login page. The first file we'll look at is login.tmpl.php. We can see right away on line 7 that the first JavaScript function on the login template page hashes the password. Looking at this function, it immediately sets the value of form password hidden to a hashed value. We also see that the form password value is hashed using SHA-1. Next, we see that our first hash value has the session token appended to it, and this entire string is then hashed a second time. At this point, we've acquired enough knowledge about the authentication process and we can implement our attack. Let's take a look at the script in the course materials that we'll use to bypass authentication. After the Python imports, the first function is called genHash, which takes two arguments, a password and a token value. Our task is to complete this function, so we'll come back to this spot later. The next function is called weCanLogin with a hash. This function does not accept any arguments, but it does build some important strings. The first is the target, which is built using the IP address or host name passed as the first command line argument. Next, we hardcode the token value to the string HAX. Line 11 shows us that the hashed value is created by calling our incomplete genHash function. Beginning on line 12, D is set to the post parameters we'll be sending to login.php. Line 18 creates a session object instance, and on line 19, the R variable is assigned the result of the post HTTP request. One important item to note here is that this is the first time we have to make use of the token value in our proof of concept. However, if we remember the application logic, if this value is sent through a POST request, it is directly assigned to the session variable token. Next, on line 20, the res or result variable is set to the value of the HTTP response body. Line 21 checks to see if we're logged in based on the content in the response and returns true or false. Finally, we see the main function checking to see if the we can log in with a hash function returns true. Okay, now that we know how this script works, let's implement our genHash function. The first thing we want to remember is how the hash is created in JavaScript. Let's add a note to this script with those details. In our comment, we see that the password is hashed first, then the token is added to the end of that value and hashed again. Since we already retrieved the SHA-1 password hash from the database, we should only need to add the token to the end of the database hash and then hash that value. Let's implement this in our script. We'll set the variable m to the hashlib object of type SHA-1. Let's use the hashlib update function to add the password hash and the token to the object. Now we just need to return the hashed value. We'll use the hex digest functionality of hashlib to properly return a string of the hash. Great. Let's save and run this script and see if we're able to log in with the extracted password hash. Excellent. Now that we've authenticated to the application, we need to see if we can take advantage of this access. Now that we've obtained authenticated access to the A-Tutor web application, our next focus is to leverage this access to obtain full control of the server. A direct way to compromise the host operating system is to find and misuse a file upload weakness. A typical file upload weakness would allow an attacker to upload malicious files to the web server, access them through a web browser, and execute commands. Many application developers anticipate this type of attack and perform validations to prevent it. Typical file upload validation methods include checking file extensions and uploading files outside of the web root. Even when developers deploy some layers of defense, there are often mistakes or oversights. A-Tutor version 2.2.1 contains at least 2 of these types of errors. We'll take advantage of one of them here. Let's log into the application using the teacher account and review the upload functionality. When we reviewed this application, we found that the Tests and Surveys section has upload functionality. We can navigate here by selecting the course name, Hacking Course. Also, make sure that the Manage slider bar is on. Next, we'll click My Tests and Surveys, and then Tests and Surveys. Good. Now we see the upload functionality. Let's quickly create a text file and try to upload it. In a local Kali terminal, we'll echo offensive security into a file named upload.txt. Now, we'll upload our text file. We receive an error stating that we've not uploaded a valid zip file, so let's try a generic zip file and see how it's processed. In your course materials, you can find a Python script that will create a generic zip file. Let's take a quick look at this script to make sure we know what's happening. We have one function in this script named buildZip. This function creates an input-output object and a zip file object. Then, within our zip file, we write the string offsec to the file poc.txt within the poc folder. Next, we create a zip named poc.zip and open it in binary write mode. Then we add the zip content to the file and close it. Let's run this script and look at the output. Great. Now that we have an example zip file, let's upload it. The zip file appears to have been accepted, but this time an error message indicates that the archive is missing an IMS manifest file. This suggests that the contents of the zip archive are being inspected as well. Therefore, we're going to have to determine what exactly an IMS manifest file is and see if we can generate one to include inside the zip archive. Guessing what the application is expecting would be very hard, if not impossible, but since we have access to the source code, let's determine if it's possible to bypass the content inspection. The first step is to identify which of the ATutor PHP files we want to audit. A good starting point is to grep for the IMS manifest file is missing error message that was returned while uploading our zip file. Our search attempt finds the error message in the installation file atutorlanguagetext.sql, which shows that the error message is defined as the constant AT_error no IMS manifest. This suggests that a good number of the application error messages are stored in the database. By looking through the code, we quickly realize that the constant naming format found in the database installation file does not quite match the error constant names used in the source code. Specifically, the AT_error prefix is omitted in the code. We can see this by running a search for the no IMS manifest constant. Now we see that our error constant is used in multiple locations in the code, indicating that if the file upload is vulnerable, there may be multiple paths to the same vulnerability. Let's focus on import test.php for now though, as this file is directly used in the import HTML form used for the upload. Now let's search for no IMS manifest. Starting on line 219, we find references to the manifest file and also see the no IMS manifest error being referenced in case the manifest file is missing. From this code, it's clear that the zip archive needs to contain a file named imsmanifest.xml, so let's go ahead and update our script to create it. Great. Our code now creates a valid and properly formatted XML file, which should be able to pass the parser checks starting on line 238 of import test.php. We can finally attempt to upload our newly generated archive with the well-formed imsmanifest.xml file inside. Let's try that now. We'll switch back to our terminal, then run our updated script to create the zip file. Great. Now let's try to upload this file to the web application. This is great. We're told that our file has been imported successfully, meaning that we've successfully crafted a zip file that meets the application's file upload requirements. Next, we have to determine if we can misuse this functionality. Since the application checks for a file within the archive, we know that the contents of the zip are extracted and inspected to some degree. Logically, that means that the uploaded archive has to be extracted at some point, and therefore, we can assume that our proof of concept file poc.txt would be located somewhere on the file system. This can be verified by searching locally on the target machine for the poc.txt file using elevated permissions in order to ensure that the entire file system is checked. Let's switch back to the ATutor server and look for this file. Sadly, we find no trace of poc.txt on the target machine. It appears that a successful import means that our zip file is extracted and then later deleted along with its contents. Let's look back to the XML validation code chunk in our text editor. Since our goal is to permanently write a file to the disk, hopefully an evil PHP file, we need to find a way to ensure that the uploading process fails just after the extraction. In fact, if we look on line 244, a failed attempt to parse the contents of the imsmanifest.xml file would actually force the PHP script to die with an error message at line 245. Assuming that no other PHP code is executed after this point, we should be able to permanently write a file of our choice to the target file system by including an improperly formed imsmanifest.xml file. It's interesting to note how our overzealous attempt to create a valid XML file actually prevented us from reaching our goal in the first attempt. Let's quickly try this approach by updating our Python zip script. Now, let's run it to create a new zip file and upload it to eTutor. This time, the response indicates that the XML file is not well formed, which seems to suggest success. Let's verify this on the target machine by again searching the entire file system for the poc.txt file. Excellent. Our uploaded file has indeed remained on the file system after being extracted. We're getting closer, but there's still a couple more hurdles we need to overcome in order to fully exploit this vulnerability. Now that we have a basic understanding of this file upload vulnerability, let's attempt to exploit it. You likely noticed that the file is extracted under the var content directory. This is the default directory that's used by eTutor for all user-managed content files. This presents a problem, as our goal is to upload arbitrary PHP files to the web directory. We'll need to escape this file system jail. The first option that comes to mind is to use a directory traversal attack to break out of this jail. Let's try this approach by updating our script to attempt to write the poc.txt file to a writable directory outside of var content. More specifically, let's attempt to write to the /tmp directory, which is writable by any user. Hopefully, this change will traverse to the parent directory and write the file to /tmp during the zip extraction process. Let's run that script again. And again, we'll upload it to the application. As expected, our upload attempt with the newly crafted archive still fails with the error message about the XML not being well formed, but this time we have hopefully written outside of the jail. Let's switch back to the eTutor server and check. Excellent. This confirms that we've escaped the var content jail. Given our progress up to this point, and with the goal of gaining remote code execution, we have to fulfill 3 more requirements. We need to know the location of the web root directory, we must gain access to a writable directory, and we must discover a file extension that can be used to execute PHP code. Since we're using a white box approach for this test case, we already know that the web root is set to var www html, but in a black box scenario, we would need to work for this. We could abuse the display errors PHP settings, which we discussed earlier, by sending a GET request with arrays injected as parameters. This technique, known as parameter pollution or parameter tampering, relies on the fact that most back-end code does not expect arrays as input data from an HTTP request and may pass that array into a function that is expecting a string data type. Since we can change the data type of the submitted parameter from a string to an array, we can trigger an error. For the sake of completeness, let's attempt this information disclosure vector on the eTutor web application. Since we've already enabled display errors, we can try the array injection attack in the browse.php file. Looking at the warnings here, we can clearly see the disclosure of the full web root path. Essentially, all we need to do is cause the application to trigger a PHP warning, which is quite common when unexpected user-controlled input is parsed. This allows us to disclose information that would otherwise be private, such as the local path of the web root on the host where the application is running. Now that we know how to find a web root path, we can move on to the next requirement before we can gain remote code execution. In a black box approach, we can find a writable directory by either brute forcing the web application paths or via another information disclosure. However, since we're using a white box approach, we can simply search for writable directories within the web root on the command line. Let's do this on the ATutor server now. Looking at the results, we see that all of our writable paths include the mods directory. The ATutor web application uses the mods directory for installation of modules performed by the administrative ATutor user. This implies that it has to be writable by the www.data web user. Let's update our script to use this directory as the target of the traversal attack we described in the previous section. We'll create this zip and verify it works as expected. Everything looks good, so now let's upload the zip file. Now that we've uploaded the zip file, we would expect that poc.txt is located in the mods directory. Let's browse there and see if we can find the file. Our uploaded zip file worked, and we can access our file. Nice. That leaves us with only one more hurdle to overcome. Based on the exercise earlier in this module from the course material, we know that the ATutor developers made an attempt to prevent the upload of arbitrary PHP files. More specifically, we know that if we include any file with the PHP extension in our zip file, the entire import will fail. Fortunately, the Apache web server can interpret a number of different files and extensions that contain PHP code. But before we arbitrarily choose a different extension for our malicious PHP file, we need to see how the ATutor developers implemented the file extension filtering. We'll find this code in the import test.php file. A quick look at the code tells us exactly how the zip file extraction process works. Specifically, the developer comment on line 177 indicates that the extract function on line 181 is using the callback function pre-import callback to filter out PHP files from the uploaded archive file. The implementation of the pre-import callback function can be found in filemanager.inc.php. Let's open that file as well. On line 170, we spot a reference to an illegal extensions array. A quick search leads us to the file constants.inc.php, where we find a number of configuration variables, with the most important for our purposes being illegal extensions. Let's take a look at that file as well. At this point, all we need to do is pick an extension that is not in the list, yet will still execute PHP code when parsed from the web server. For this exercise, we'll choose PHTML among the many other workable extensions available to us. All that remains for us is to update our script so that it generates a proof of concept file with the PHTML extension and add PHP code to it. Let's update our zip creation script now. In this proof of concept, we're injecting the PHP code php-info. Let's generate our zip file. Now, let's upload our file to ATutor. Finally, we can test if our file was uploaded. Excellent. After running through our entire attack vector, we have arbitrary PHP code execution. Now, let's leverage this vulnerability to obtain a reverse shell. First, let's validate our attacking IP address. Next, we'll add malicious PHP to our zip file creation. This PHP code uses bash and the sudo device dev-tcp to initiate a connection and send a shell back to our listener. Here we can change the attacker IP address section to reflect our IP address. Now we can save and create the zip file. Let's try uploading our newest zip file to ATutor. Now we need to open a netcat listener on port 4444 in order to receive our reverse shell, so let's set that up next. Now, let's execute our PHP script and see if we get a reverse shell. Excellent. Our netcat listener caught the reverse shell. After running through our entire attack vector, we can see that we have arbitrary PHP code execution, which results in a reverse shell. In this module, we've explored a number of different vulnerabilities which we were able to combine into a powerful exploit. We first discovered a pre-authenticated blind SQL injection that allowed us to exfiltrate arbitrary data from the ATutor database. We then thoroughly studied the application authentication mechanism and discovered a flaw that, when combined with the SQL injection, allowed us to gather privileged access within the ATutor platform. Leveraging this access, we identified and exploited a post-authentication file upload vulnerability that provided us with a remote shell on the target server. The vulnerability chaining concept is important to keep in mind, as modern web applications often require the use of multiple vulnerabilities when being exploited. ATutor LMS type juggling vulnerability. In this module, we'll cover the analysis and exploitation of a PHP type juggling vulnerability in ATutor version 2.2.1, which we'll use to gain privileged access to the application. The ATutor admin interface can be accessed using the IP address and credentials from your student control panel. To make things easier to follow, we've updated our hosts file to use the ATutor host name rather than the IP address. We'll log in with the username teacher and teacher123 as the password. The vulnerability in this module revolves around the use of loose comparisons of user-controlled values. Ultimately, this will allow us to subvert the application logic and perform protected operations. Before diving into the actual vulnerability, we need to understand how type juggling can cause potential problems. In PHP, a variable's type is determined by the context in which the variable is used. If a string value is assigned to a variable, then the variable becomes a string type. While this can be seen as a good language construct, it becomes a difficult road to navigate when dealing with comparison operations. As we'll see, type juggling can sometimes diminish the protection of sensitive operations. Because of this, newer versions of PHP have the concept of strict comparisons, which compare both the data values and the types associated to them. To better understand the concepts discussed in this module, we also need to look at the PHP string-to-integer conversion rules. According to the PHP manual, when a string is evaluated in a numeric context, the resulting value and type are determined as follows. If the string does not contain a period, lowercase e, or capital E, and the numeric value fits into the integer type limits, the string will be evaluated as an integer. Otherwise, it will be evaluated as a float. The value assigned is determined by the initial portion of the string. If the string starts with a valid numeric value, then this will be the value assigned. Otherwise, the value will be 0. Let's try a few examples to illustrate what this means in practice. First, let's SSH to our ATutor virtual machine. First, we'll check the PHP version of ATutor. This server is running PHP 5. Let's keep that in mind. Next, let's run PHP in interactive mode and perform a few loose comparison operations. In these examples, we'll use the decimal number 43,690, which is equal to 4 A characters in hexadecimal. We'll first compare them both as strings, then as a string and an integer, then as a hex representation and integer, and lastly, we'll compare two different values to make sure that comparisons actually work. As you can see, PHP attempts to perform an implicit string-to-integer conversion during the loose comparison with hexadecimal notation. Let's open another tab and try the same comparisons on our Kali machine, which is running PHP 7. We'll run PHP in interactive mode again, and run the same comparisons as last time. As we can see, more recent versions of PHP return very different results in an attempt to minimize loose comparison-related problems. The most interesting conversion rules for the specific vulnerability we're going to explore in this module revolves around the scientific exponential number notation. The PHP manual states that anytime a string beginning with one or more digits, followed by the letter E, followed by one or more additional digits, is used in a numeric context, such as a comparison to another number, that string will be evaluated as a number. Let's look at this in practice. We'll start with an example, comparing a scientific notation string with an invalid exponent with the string 0. As expected, the comparison returns false. However, if we compare the string 0 to a string containing a properly formatted exponential notation, PHP evaluates both strings as numbers and returns true. The same holds true if we compare a string to an integer. This confirms that the automatic string-to-integer conversion is working as expected, even when the exponential notation is involved. Note that the PHP version is irrelevant here. These examples would work identically in PHP 7 since the interpretation rules for exponential notations have not changed in newer PHP versions. But why does this matter to us? Let's take a look at our vulnerability and see how we can take advantage of loose comparisons when scientific exponential notation is involved. In the previous ATutor module, we obtained privileged access to the application using a combination of SQL injection and flawed authentication logic, but this is not the only way to obtain privileged access. It turns out that an unauthenticated attacker could gain similar access by leveraging a type juggling vulnerability in the ATutor codebase. Specifically, to exploit this vulnerability, an attacker must reach the code segment responsible for user account email address updates, located in confirm.php, which is publicly accessible. Let's take a closer look at the logic behind the email address update confirmation process. This code segment can be found in the confirm.php file starting on line 25. On this line, the GET request variables E, ID, and M need to be set in order for us to enter this code branch. Line 28 refers to the familiar add slashes function from the previous ATutor module. In this case, add slashes resolves to the trim function, but even if it was sanitizing input, it wouldn't affect this vulnerability. Lines 30 and 31 perform an SQL query that uses the ID value passed in the GET request. Notice, however, that this value is typecast to an integer on line 26. Furthermore, line 33 checks that the ID value corresponds to an existing entry in the database by testing for the presence of the creation date value within the result set. This makes sense given that one of the functions of confirm.php is to update email addresses of existing users. Before continuing, let's inspect the ATutor database table involved in the SQL query. We'll log into the MySQL database using the default root tor credentials. Then we'll switch to the ATutor database and look at the table involved in the SQL query. Our target for the purpose of this exercise is the teacher account, with the member ID value equal to 1. Since we're targeting the account with ID value 1, the query will return a single row, and the creation date array entry will be populated, allowing us to pass the check on line 33. On line 34, the code variable is initialized with the MD5 hash of a concatenated string that consists of two controlled values, E and ID, along with the creation date value returned by the SQL query. More importantly, only a substring of the first 10 characters of the MD5 hash is assigned to the code variable. Finally, on line 35, we see a loose comparison between the M variable that is under our control and the code variable, which we partially control. If we find a way to enter this branch, we would then be able to update the target account email as seen on lines 37 and 38. And finally, on line 40, we would be redirected using the PHP header function to the target user's profile page. From here, once the email is updated, we can request a password reset. To quickly summarize what we know so far, confirm.php is used to change the email address of an existing user and can be accessed without authentication. From our code analysis, we also know that in the code that updates an existing email address, the ID get variable is the unique ID assigned to each ATutor user in the database. The get variable is the new email address we want to set. The get variable is used to decide if we are allowed to update the email address for the target user through a loose comparison against the calculated code variable. Finally, ID, E, and M are under our control, while code is partially under our control. In order to uncover an attack vector against the loose comparison discussed in the previous section, we'll need to recall what we've learned about the PHP scientific exponent notation and introduce the concept of magic hashes. Loose comparisons can play a significant role when they're used in conjunction with hash values like MD5 or SHA-1. The hexadecimal characters used to represent various hash types are the upper and lowercase letters A through F and the digits 0 through 9. This means that it may be possible to discover a plain text value whose MD5 hash conforms to the format of scientific exponent notation. This is also true in the case of MD5, and researchers have already discovered the specific string. Let's quickly take a look at loose comparison using this magic string. This MD5 hash looks like an exponential number. Let's compare it to 0. The MD5 of this particular string translates to a valid number formatted in the scientific exponential notation, and it evaluates to 0. Interesting. Based on this, if a value we control is hashed with MD5, then processed using loose comparisons, we could subvert the code logic due to this unexpected numerical evaluation. Let's now move on to our specific case and figure out if there's a way to craft a similar magic hash to specifically abuse this loose comparison. From the previous section, we know that if we could force the target application to generate a code variable in the form of a magic hash, we would be able to bypass the check on line 35. This is true as we have full control over the m variable, which we could set to 0 or the appropriate numerical value depending on the obtained magic hash. Unfortunately, since we do not fully control the code variable, we'll have to use a brute force approach. This should be relatively simple because the unique code consists of only the first 10 characters of an MD5 hash. While crafting our requests, we need to keep in mind that the account creation date is a static value pulled from the database, and the account ID is static as well, since we're targeting a single account. The only dynamic part of the concatenated string is the e variable, which holds the email address that we'll provide as a GET_REQUEST variable in each brute force attempt. Before implementing a live attack against the server, let's attempt to recreate the code logic in a Python script and see if our plan is feasible. The script will generate all possible combinations of an email username within the length limit we specify, and try to find an instance in which the 10-character MD5 substring of the full email address starts with a 0E followed by digits. Again, if we find such a magic hash, given that we control the m variable and we can set it to 0 in our GET request, we can exploit the loose comparison and enter the if block to update the email address to the address generated by our brute force attack. One important aspect to keep in mind while exploiting this vulnerability is that we'll need to generate an arbitrary email account for a domain we control. This is necessary because after we update the email address, we'll use the Forgot Your Password feature to have a password reset email sent to that address, which will ultimately allow us to hijack the account. Let's inspect our Python script. The function responsible for the email address generation takes 4 arguments: the domain name, the target account ID, a creation date, and the character length of the email username. It then starts generating all possible combinations of email addresses using only the alpha character set and performs the MD5 hash on the concatenated string. If the 10-character substring matches our criteria to pass the loose comparison, the script will mark the email as being valid. Let's run the script and take a look at the output. To validate our process and demonstrate that our brute force approach can succeed relatively quickly, we'll use the real creation date value. Note that we will not need to know this information prior to our brute force attack against the ATutor server, as it will be returned by the database during the server-side validation process. Let's run the script. Nice. Our script found a valid email address. As we can see, it took roughly 2,000 attempts to find a valid email address, which is a relatively small number of iterations for a brute force attack. Now, let's attempt our attack against the ATutor server itself. The script we'll use is similar to the previous one, except that it makes an HTTP request to the ATutor server on each iteration. If you recall from the source code analysis, a successful account email update is followed by a redirect to the user's profile page. Knowing this, our script determines success based on a returned HTTP 302 response. Before executing our script, let's verify the current email of the targeted teacher account. Now, we'll execute our new script and see if we can hijack the account. A quick look at the ATutor administrative interface confirms the success of our attack. Excellent. Now we can reset the password for the teacher account and we'll have successfully gained unauthorized privileged access to ATutor. In order to make sure that the ATutor application will send the email correctly, we'll update its local postfix configuration to use the @mail server. In a live attack, we would not need to perform this specific configuration, but it's required within our lab. We'll return to the ATutor SSH session and update the transport configuration in postfix. In our instance, the @mail server's IP address is 192.168.121.106. It'll be different in each lab and should be adjusted based on your course materials. Now we'll save and close the transport file and generate the Berkeley DB file. Finally, we'll restart the postfix service on the ATutor server. Now that the ATutor server can send email to the @mail server, we can create the email account in @mail. We'll begin by opening a new tab in our browser and logging into the @mail administrative application. Now we'll create the email account that we were able to update. We'll create the user, and we can now conveniently log into the account. Great. Now that we've created the account, we can submit the password reset on ATutor, and we should get an email in our hijacked offsec.local email account. Let's switch back to the ATutor browser tab and request the password reset. Now we can use the link provided to change the teacher password. Let's copy and paste this link into a new tab and enter a new password of offsec123. Now we should be able to log in with the credentials teacher offsec123. Excellent. After resetting the password, we can now execute the same file upload attack as we did in the previous ATutor module to gain unauthorized access to the operating system. As we've seen in this module, type juggling vulnerabilities can provide us with another vector against PHP web applications that is more likely to get overlooked by developers than more commonly known techniques such as SQL injections. Nevertheless, given the right circumstances, these vulnerabilities can be just as powerful, and we should always be looking out for loose comparisons when reviewing PHP applications. Manage Engine Applications Manager SQL Injection. The following module will cover an interesting SQL injection vulnerability in the Manage Engine Applications Manager software. The exploitation of this vulnerability is especially interesting since we're using less common techniques which ultimately result in a remote code execution under NT authority context. In addition, this module will also discuss and demonstrate ways in which we can audit compiled Java servlets to detect and uncover similar vulnerabilities. The Manage Engine Applications Manager is an application that is designed to monitor the performance and uptime of critical applications in an organization's infrastructure. This makes the server running this software a valuable target. The application can store sensitive information about other applications, or the operating system may have cached credentials of a privileged user in the environment. Let's get started and make sure we can access the vulnerable application and set it up for our inspection. We'll first remote desktop to the server where we installed the Manage Engine Application Manager. Check your lab guide for the remote desktop credentials. Now that we're on the Manage Engine server, we'll open up a browser and navigate to the Manage Engine Administrative Interface. We know that the interface is running on port 8443 since this was the default installation option. We'll accept the server certificate. Good. This is the Manage Engine login interface. In order to familiarize ourselves with the application and test that it's working correctly, we'll log in using the default credentials, username admin and password admin. Next, close the Setup dialog box. Great! Now that we've verified the very basic functionality of the application's web interface, let's examine the back-end database of the Manage Engine system. During this module, we'll have to explore the application and its interaction with the database. This will require us to execute SQL queries. While installing Manage Engine, we chose to use a Postgres database, which was the default option. In order to graphically navigate the Postgres database, we'll use a convenient Postgres client called pgadmin. We'll use it to connect to the local Manage Engine Postgres instance. Let's open pgadmin now. Once we expand the servers, we'll see the default instance is named AMDB. If we expand that, we'll also see that there is an AMDB database. Let's expand these entries to see the schemas and public AMDB database tables, which are located within the AMDB database. Lastly, we'll expand the Tables option. Within pgadmin, there's a query tool that will allow us to execute SQL statements. Let's perform a simple query against the AMDB database table admin config. We can open the query tool by right-clicking the admin config table and choosing Query Tool. Now that we have the query tool open, let's enter our query to select all items from the admin config table. We do this by entering the query select star from, and then we add our table name, admin config. Next, we'll execute the query by clicking Execute, the button with the lightning bolt icon. Good. Now we can see the contents of the admin config table. If we use this query during our testing, we'll know to expect 6 rows of return data. We've confirmed that the application is running, and we have access to the underlying database. We're now ready to start poking at the application to see if we can uncover any vulnerabilities. Whenever we start auditing an unfamiliar web application, we first need to familiarize ourselves with the target and get an idea about the exposed attack surface. By browsing through the Manage Engine's Application Manager web interface, we can see that most URLs contain the .do extension. A quick Google search shows that the .do extension is typically used in a URL mapping scheme for compiled Java code. Now that we know this is a Java application, let's see what else we can discover. We'll start by launching Process Explorer to gain additional insight into the Java processes we are targeting. Let's do that now by using the taskbar icon. The question is, how do we know which Java process to target? Let's sort by the process name and take a look. Fortunately, there is only one Java process running on our vulnerable machine. Some applications will utilize multiple Java processes to run an application. If we have multiple processes, we can get more information by right-clicking and choosing Properties. Let's do that now. Before we continue, note that the user of the Java process is NT Authority System. This means that successfully exploiting this service would lead to a complete server compromise. In the path location, we can see that the process uses the working directory located in C Program Files x86 Manage Engine App Manager 12. This confirms that we're on the right track and the Java process is from the Manage Engine application. This is a good place to start looking for additional information about our target application. Let's open that directory. Java web applications use a deployment descriptor file named web.xml to determine how URLs map to servlets, which URLs require authentication, and other information. This file is essential when we look for the implementation of any functionality that this web application exposes. Within the working directory, we see a webinf folder, which is Java's default configuration folder path, where we can find the web.xml file. Let's open it up and take a look. If we scroll down to about line 215, we can see the name of the servlet classes that are mapped to servlet names. We can also see what URL is mapped to which servlet, which we'll need if and when we find an exploitable vulnerability. Now that we have a better idea about this application and how it's laid out, we can start thinking about how to look for any potential vulnerabilities. We'll begin by looking for SQL injections. As we already discovered from the initial review, at least some components of the Manage Engine Application Manager are written in Java. Fortunately, compiled Java classes can be easily decompiled using publicly available software. But we first need to identify which Java class or classes we want to review. Looking inside the webinf directory, we see a lib directory, which contains a number of jar files. If we look at the file names, we can see that most of them are actually standard third-party libraries, such as struts and XML-sec jar files. Only 4 jar files in this directory appear to be native to Manage Engine. And of those 4 files, the Advent Net App Manager Web Client jar file looks like a good starting point thanks to the rather self-explanatory name. Let's take a look at this file. As we saw in the Tools and Methodologies module, we can use JDGUI to parse jar files and decompile the classes within. Let's open JDGUI by clicking on the icon in the taskbar. Once we decompile this jar file, we quickly notice that it contains a rather large collection of Java classes. This means we need to develop a process which will help us with source code review. Otherwise, we may end up spending a lot of time looking at portions of the source code that may not be valuable to us. As already mentioned, although JDGUI is an excellent decompiler, its search capabilities could be better. Since we already have Notepad++ on our target machine, we can use that to help us navigate this codebase in a more efficient way. First, we'll need to save the decompiled source code into human-readable Java files. JDGUI allows us to do that via the File, Save All Sources menu. Let's try that out. We'll navigate to the desktop and click Save. Great. Now let's take a look at the desktop. The only thing left for us to do is to decompress the saved source code files we just extracted, and we'll be ready for our code audit. Let's validate that our source extraction worked correctly. We'll open a folder that contains an extracted .java source file. Let's use the Advent NetApp Manager Web Client jar source folder. It looks like we've successfully exported Java source code. We're now able to use Notepad++ more efficient search capabilities along with JD-GUI for code navigation. So let's start thinking about what we need to look for in this code. With our tooling in place, we need a plan for finding any potential vulnerabilities, starting with SQL injections. A natural first step is to find all instances of an SQL query string, then identify any user-controlled input that is contained in those queries, since this can potentially lead to a SQL injection vulnerability. So let's first search for select queries. Notepad++ also allows us to use regular expressions, which will hopefully minimize the number of false positives we encounter. We'll begin with a simple search. We'll open Notepad++ and select the Search menu, then Find in Files, or we can use the Ctrl-Shift-F shortcut. Now that we have the Find in Files dialog open, we'll type Select in the Find What box. Next, we'll make sure that our directory is set by clicking the Browse for Folder button, and we'll scroll down to the Advent NetApp Manager Web Client jar source folder. Lastly, we'll make sure that In All Subfolders is checked. Now, let's click Find All. Okay, so we found quite a few results for Select within the selected source code folder. We need to reduce this to something much more usable for our discovery. Let's try another search, but refine it to only include SQL statements. First, let's remove the search history. We'll go to the search menu again and select the Find in Files option. In this case, our search string looks like this. The reason we chose this particular regular expression is because we noticed that most query strings in the code are assigned to a variable named query. If you're not familiar with regular expressions, spend some time learning them. Regular expressions are very useful during vulnerability discovery, but for now, just know that this expression basically says, look for any line that begins with any number of alphanumeric characters, which is followed by the string query, which is followed by a number of any character, which is followed by the string select, which is followed by a number of any characters. This may sound complicated, but let's jump in, execute the search, and visualize what it means. Before we do this, however, let's make sure that the regular expression option is checked and that the directory text box is pointing to the directory on our desktop that contains the extracted Java source code files. Now, let's search and take a closer look at the first result. As we can see, this line contains the strings query and select in that order, with any number of characters between and around them matching our regular expression. Now, let's have a look at how many queries were found in the source code. Our search returned almost 5,000 instances of select queries in this jar file alone. This attack surface is still very broad. We could jump right in, but to avoid becoming overwhelmed, let's come up with a better approach to reduce the attack surface. One approach when reviewing a web application is to start from the front-end user interface implementation and review the HTTP request handlers first. In a typical Java servlet, we can find these functions by searching for their constant and unique names. The function names start with the prefix DO, followed by the request type name. DoGet and DoPost are just two examples. Let's take a look at a sample search. only 87 hits. This is a more reasonable starting point. Now we can focus on this much smaller attack surface and look for any instance of the do-get implementation that uses user-controlled input in an SQL query string. Keep in mind that this process also includes tracing user-controlled input through subsequent function calls, if these values happen to be passed on. After spending a bit of time following this process through a number of classes, we arrive at the do-get implementation of the AM User Resources Sync Servlet class. Let's open this class in JDGUI and take a closer look. We can either use the class path from the Notepad++ search results, or we can quickly go back to the web XML file where we find the following mappings for this class. Let's find that class in JDGUI. As is typical, the do-get function expects two parameters, the request and the response. The first parameter is an HTTP servlet request object that contains the request the client has made to the web application. The second is an HTTP servlet response object that contains a response that the servlet will send to the client after the request is processed. We're particularly interested in the HTTP servlet request object, since that is what we can control. Now that we're familiar with how HTTP requests are processed in a Java servlet, let's dive straight into the do-post and do-get methods in the AM User Resources Sync Servlet class. Looking at this code, there are a number of things we need to understand. First of all, we can see that the do-post method redirects to do-get. In servlet implementations, it's common to see multiple HTTP verbs handled by a single method. In the do-get function, we can see on lines 31, 37, 38, and 39 that 4 different user-controlled parameters are retrieved from the HTTP request. Is sync config to user map, for mass range, user ID, and check restricted role. We can use syntax highlighting in JDGUI to highlight variable instances. If we double-click on any variable name, the application will highlight this variable in the code. Let's try that with the variable user ID. This variable is used in a few places, but if we scroll down just a bit, we can see that it is used directly in a select query string through concatenation. Depending on the sanitization of the user ID variable, this looks like a good SQL injection candidate. However, we're in a different function now, and we need to figure out how to get here through the code. If we double-click on the function name, we can clearly see that it is called from the do-get function we started with. So let's go back to the beginning of do-get and work our way through. If luck is on our side, this variable will be fully under our control and hopefully not sanitized. First of all, we need to concern ourselves with the first and second if statements on lines 32 and 42 respectively. Specifically, if they would evaluate to true, we would not be able to reach the else if on line 49, which is where we need to land. If we look at these if statements, we can see that we should be able to control which conditional branch we take, since they depend on the user input in an HTTP request. In both cases, the first check is whether the respective variables that we control are null. This means we have to make sure that in our malicious requests, those parameters are not set. This should allow us to fall through to our target statement on line 49. Speaking of which, the else if statement on line 49 checks for the presence of the mass range variable and only moves on to the next if statement if it exists. So we need to make sure that our request has the for mass range parameter set, which happens on line 37. Finally, we arrive at the last if statement on line 50, which follows the same pattern. It too will check for the presence of the user ID variable and make sure it's not an empty string. We've now completed the entire analysis to finally arrive at the fetch user resources of mass for user ID function call. Best of all, we did not see any sanitization of the user ID variable. And since no such attempt is performed in the fetch user resources of mass for user ID function, there is almost certainly a vulnerability here. Very nice. We've completed our analysis at this point and verified that we indeed have a likely SQL injection vulnerability we can attempt to exploit. Now, let's start validating our findings. We've successfully reviewed the application components and its supporting technologies. We've also extracted and analyzed the source code to find a likely candidate for SQL injection. Now we need to validate this vulnerability. In order to validate and exploit this potential SQL injection, we need visibility into the execution of database queries. Specifically, we need to know which of our queries are successful and which queries cause errors. We can do this by enabling database logging. Database logging can save us a lot of time while debugging applications, especially when we're dealing with possible SQL injection vulnerabilities. In this instance, we already know what the vulnerable query looks like. However, we need to see if any injected characters are stripped or transformed by the application before they reach the database level. Since Manage Engine uses Postgres as a backend database, we'll need to edit its configuration file in order to enable the logging feature. In our virtual machine, the Postgres configuration file is located at the following path. We're looking for the log statement setting, which we can locate using the find command. Changing the log statement setting to all will instruct the database to log all SQL queries. After changing the logging setting, we need to restart the Manage Engine Applications Manager service to apply it. We can do this by starting services.msc and restarting the Manage Engine Applications Manager service. Let's do that now. The log files are created in the format PostgreSQL_ followed by a number and a .log extension. Now that we've enabled more verbose logging, let's take a look and be sure that our changes worked. We'll open both a PowerShell terminal and the pgadmin application to test that our queries are being recorded in the log files. Let's open the pgadmin program and navigate to the AMDB database. Right-click the database and choose the Query tool. For our example, we're going to run a simple query to extract the version of Postgres by typing the following. Before we execute the query, we're going to open a PowerShell prompt and use that terminal to see if our query is being recorded in the logs. Let's open the PowerShell terminal from the taskbar. Next, we'll navigate to the pgsql_log directory. Let's grab a directory listing. We'll likely find a number of log files in this directory. The log file with the highest number is often the most recent. However, keep in mind that the number is based on the calendar day. For example, if you're looking at these log files on the first day of the month, the file PostgreSQL_1.log file will be the most recent. In order to list out the most recently updated file, we'll issue the following command. This command pipes the directory listing through the sort command, which sorts by the last write time. This output is piped into the select command, which will return the last item, the file we want to search for our SQL query. Now that we know which file we want to review, we can run a PowerShell command that will constantly display the new contents of this file and only select the lines that match our criteria. Let's do that now. In this command, we'll use the log file number from the previous command and show any new lines added to that file. This command will show all new log file entries. However, we've seen that Postgres updates this log file quite frequently. In order to filter out the log entries we're interested in, we can add an additional command. Specifically, we'll add a pipe command which will redirect the output of our first command for additional filtering. This will only display the entries corresponding to our queries. Now, let's go back to pgadmin and run the query select version. We see that it was successful, so let's check our PowerShell window to make sure that our query has been recorded in the logs. Excellent. The log file entry confirms that our query monitoring setup is working. Now that we've enabled database logging, we can continue validating the potential SQL injection. We must actually trigger the vulnerability in order to make further progress. From the servlet mapping in the web XML file, we know that the URL we need to use to reach the vulnerable code is servlet am user resources sync servlet. Alright, let's go back to our source code analysis for a moment. During our analysis, we found that two parameters, for mass range and user ID, are required to reach the vulnerable SQL query. Let's switch to our Kali attack machine and try to send our initial proof of concept payload. We'll use the burp suite as our intercepting proxy to make our development process easier. Let's launch Firefox and burp suite. If you haven't done so already, make sure that your Kali Firefox installation is configured to use a proxy on local port 8080, the default burp suite port. We've already done that, so we can continue. In our browser window, we'll go to the following URL. Notice that the request we use performs a simple injection using a semicolon. This is because we know from our analysis that the vulnerable query does not contain any quoted strings, and therefore we can simply terminate the query with a semicolon at the injection point. Let's hit enter in Firefox to submit the URL. Then we'll check burp, turn intercept off, and look for the response received from the server. Interesting. It looks like the response is empty as indicated by a content length of 0. This is worth noting because in the case of a black box test, we would almost have no way of knowing that a SQL injection vulnerability even exists. We'll talk about this a bit more shortly, but with a content length of 0, no verbose errors, no post body changes, and no 500 status codes, at first glance everything seems okay. Nevertheless, let's take a quick look at our Postgres log files and see what we have there. Because the Postgres log file is being updated constantly, we'll specifically filter out lines with the term resource ID and syntax error. This is because our vulnerable query contains the term resource ID, and we're also looking for errors, since our payload terminates the SQL statement before its expected end. First, let's see which log file has been most recently updated. Great. Let's check and see if this file contains the vulnerable query and any errors. We'll use the following command to show the last 100 lines and display only lines containing either resource ID or syntax error. Again, we recommend that you investigate regular expressions further to fully understand the pattern value we're using here. This command may return varied results if significant time has passed between your payload submission and running the command. If you don't see the key results, simply increase the tail value. When we look at our command results, we see an error message that clearly indicates a SQL injection. If we remember the vulnerable query we discovered earlier, we can see that the injected semicolon terminated the vulnerable query after user ID equals 1. The remainder of the query, beginning with and resource ID greater than 1, is treated as a second or stacked query and causes an error since it's not a valid SQL statement. If we pay close attention to the vulnerable query, we can see that we have a few options for the type of payload we can inject. One approach would be to use a union query and extract data directly from the database. However, we need to be mindful of the fact that the resource ID column that the original query is referencing is defined as a big int data type. In other words, we could only extract arbitrary data that is also of the same data type. The other option is to use a union query with a Boolean-based blind injection. Similar to what we've already seen in ATutor, we could construct the injected queries to ask a series of true and false questions and infer the data we're trying to extract in that fashion. Although this approach would work for data extraction, we won't describe it in detail here, and we'll leave it as an exercise to demonstrate its feasibility. The reason we're not considering this approach is because one of the great things about Postgres SQL injection attacks is that they allow an attacker to perform stacked queries. This means we can use a terminator character in our payload and inject a completely new query into the original vulnerable query string. This makes exploitation much easier since neither the injection point nor the payload are limited by the nature of the vulnerable query. The only downside with stacked queries is that they return multiple result sets, which can break the logic of the application, and with it, the ability to exfiltrate data with a Boolean blind-based attack. This is unfortunately exactly what happens with our Manage Engine application, and you can find more details about this in your coursebook. In order to solve this problem and still be able to use the flexibility of stacked queries, we have to resort to time-based injection payloads. Knowing this, we'll return to our attacking machine. Since we've chosen to use a time-based injection in Postgres, we can use the pgsleep function to verify the existence of an actual vulnerability. Before we do that, let's quickly highlight our initial request in burp and send it to the repeater tab. We can switch to that tab and edit the request by introducing the following payload. Note the addition of pgsleep. Let's hit enter and execute it. Great. As we can see in the lower right, it took several seconds for the response to come back. Note that the plus between select and pgsleep will be interpreted as a space. This could also be substituted with the %20 characters, which are the URL encoded equivalent of a space. Now that we've verified our ability to execute stacked queries along with time-based blind injection, we can continue our exploit development. The ability to use stacked queries in the payload is very powerful. However, after testing various payloads, specifically those that include single quoted strings, we noticed something strange. Let's take a look at the following simple example in which we inject a single quote in the query and see what happens. To inspect our log file, we'll use a PowerShell command that is very similar to the previous example, except this time the pattern we're searching for is error, and the context flag allows us to include 2 lines after our match. The log file shows a different error this time. Let's review our vulnerable query again and focus on the log entry where we have our injected payload. We can see that our injected single quote has been HTML encoded. It also turns out that some other special characters are HTML encoded before they're sent to the database for further processing. This is definitely a problem, as it seems that we cannot use quoted string values in our queries. If we were dealing with a MySQL database backend, this issue could be solved easily using the hex representation of the string we would like to inject. Unfortunately, this feature is not present in Postgres. With this in mind, we reviewed the Postgres documentation for string manipulation functions and discovered that most functions used for encoding and decoding of various data formats, such as hex or base64, make use of quotes. In other words, the problem of quoted strings is something we really need to figure out if we want to make a fully functioning exploit for this vulnerability. Encoding evasion is not a new problem. Let's revisit at least one well-known way of bypassing character restrictions using the chur function and concatenation syntax. For example, in most situations, we can select individual characters using their code points, which are simply numbers that represent characters, and concatenate them together using the double pipe operator. When we pass the numeric code value of arbitrary characters to the chur function, it will return the ASCII representation of that character. Let's look at an example. You can do this in pgadmin if you like, but for now we'll demonstrate this using the psql command line tool. So let's open up a command prompt and start psql. On your virtual machine, it should already be in the path. Remember that the Manage Engine Postgres instance is listening on port 15432. All right, let's first connect to our database instance using the credentials Postgres App Manager. Now that we've successfully connected to Postgres, let's execute a few queries that will reintroduce us to the chur and ASCII functions and how we can eventually use them to bypass the HTML encoding restriction. Let's create a query that will select 4 ASCII values for the letter W, 2 zeros, and the letter T. Let's execute that query now. As a result, the letter W is translated to the code point 119, 0 to 48, and T to 116. Now, let's try an example where we take these numbers and translate them back to characters. Great. We see the relationship between the code points and string characters and how to use the ASCII and chur functions to convert between these two different representations. We can see that the result of this query is the string woot and that it did not use any single quotes. Unfortunately, this is not the last challenge. The problem is that character concatenation only works for basic queries such as select, insert, delete, etc. It does not work for all SQL statements. Let's demonstrate that with a different example. This time, we'll use an SQL statement that creates a temporary table called tempTable containing a single column of text and successfully inserts a record into it. Okay, great. We've performed an insert. Now, let's take a look at those values. Good. This is a slightly more complex example that still works. Notice that we're using the create, insert, and select statements. However, if we try to execute any function, for example, the copy function, using chur to write to a file, the query will fail. To demonstrate, let's write to the file cfile with a straight copy. Good. Now that we copied the contents of the table tempTable into a file, let's delete the file and try the same example using the chur function. In this query, we use the relative code points for the cfile string. However, the error we obtained indicates that we still do not have a fully functioning solution for our character restriction problem. While the chur function can be very helpful when dealing with non-printable characters, we need to find a better way to bypass the quotes restrictions for those situations where we have to make use of more advanced Postgres functions, such as copy. But not all is lost. Let's continue. After spending some time reading the Postgres documentation related to lexical structure, we discovered that Postgres syntax also supports $ quoted string constants. The purpose of this syntax is to make it easier to read statements which contain strings with literal quotes. Basically, this syntax can be used as a replacement for single quoted strings. Let's look at the following 3 examples, which will all produce the same results. Essentially, 2 $ characters can encapsulate an optional tag. Alternatively, the tag string can be entirely omitted. If a tag is used, it is then required at the end of the string as well. Let's try to execute the same copy-to query as before, but this time using the $$ syntax. Beautiful. We now know how to bypass the single quote restriction we encountered earlier, and we can also use this bypass method with any native Postgres function. Now it's time to put theory into practice. So let's get to it. Now that we have all of our tools and methods worked out in theory, let's try to attack the application and see how far we can take it. So far, we've mostly played with unterminated queries to understand the limitations in the attacker-provided input. We have, however, briefly shown how to use stacked queries in our payload when we tested the blind SQL injection vulnerability with the help of the PG sleep function. As a first step, we have to validate that our quotes restrictions bypass works in practice and not only in theory. We'll do that by sending a payload that will reveal the database privileges the vulnerable application is running with. This is very important because if the application is running with database administrator privileges, we will likely be able to do far more than simply retrieve data from the vulnerable database. This includes the ability to interact with the file system and potentially load third-party Postgres extensions. First of all, let's try to develop a working Postgres payload that will reveal whether or not we're running as DBA. Postgres provides a function called current_setting, which returns the setting value for any valid parameter that is passed to it. So to find out if we're operating under the context of a database administrator, we would execute the following query. The result is the string on, which indicates that we are database administrator. To be able to use the query we just tested in a time-based SQL injection attack, we could use a conditional statement to test the result string in conjunction with the PG sleep function. Let's run a quick query implementing this logic while avoiding single quotes. Excellent. The query slept for 5 seconds, indicating that the is_superuser setting is set to on. Let's see how this query would look in our SQL injection vulnerability. In the burp suite repeater, we'll update the URL to include our query. As before, the injected query will sleep for 5 seconds only if the is_superuser setting from the current setting table is set to on. Let's send this request to our target VM and see what happens. Look at that. The application took roughly 5 seconds to return a response, which confirms that the injection properly bypassed the quotes restrictions. Also, we can see that we're operating under the DBA context. This opens the door to more powerful attack possibilities, so let's explore them. While getting access to all the information contained in the Manage Engine database would be a good achievement, we're operating under the privileges of the DBA user. As DBA, we have access to far more powerful functionality than simply manipulating or reading information from the database. In these situations, our goal is typically to gain system access, which can be done by using native database functionality to read and write to the file system. So how do we accomplish this? In order for us to access the file system, we need to develop a different kind of valid injection query. Once again, we'll take advantage of stacked queries in our attack. Earlier, we used the Postgres function called copy, which is used to import and export data using a table and a file. That is a rather loose definition, and in the case of copy 2, we do not need a valid table as our source. The following query demonstrates this idea. We'll use a subquery select statement, set our source to a string constant enclosed between two $signs, and write this string to a file on the file system. Now we can quickly verify in Windows Explorer that this file has indeed been created and that it contains our string. We'll look for our file in the user's public folder. Let's open this file in Notepad++ to see if our query worked. Nice. We've proven that we can write files, but we can also use this vulnerability to read them, although it's slightly more complex. Reading a file will require us to create a table, select data from a file into that table, select the contents of that table, and then delete the table. Let's see how that works. First, we'll make sure that the table we want to create, in this case a table called read_file, does not exist by executing a quick select query to select all entries from that table. We can do that with the following query. Based on the error, the table does not exist, so let's create it, copy the contents of the file we created in the previous example into it, and finally check its contents. To create the table, we'll enter the following query. Good. We created the table, so let's read from our file and enter its contents into the table. This should have copied the file's contents into our table. We can confirm this process worked by running the following query. Great, it worked. Now let's delete the table from the database using drop table read_file. We can quickly verify that the table was deleted by trying to select it again. Now, let's attempt to implement this example in our injection payload. Our injected query will create the read file table and insert the content of our test file into it. Then it will try to verify that the first letter of the string that we inserted into our read file table is the letter A. Since we can't directly read the data from the file in the server's response, our request will once again use a time-based comparison to infer the data. If the comparison evaluates to true, the query will sleep for 5 seconds. In Burp Suite's repeater, we'll update the URL with our new query and send it off to the server. Beautiful. The delayed response confirms that our logic is sound. Using this technique, we can extract the contents of any file. Notice how in this case we're using the substring and ASCII functions to achieve our goal. While substring helps us reading the file content byte by byte, ASCII ensures that we avoid any encoding issues. This is especially important when reading binary files. Let's take this idea of file system interaction a bit further. Our next goal is to write from our machine to the target's file system. We've already seen how to do that from the PSQL client, so let's develop a payload that will write a file to the root directory of the C drive on the vulnerable server using the copy_to function. We'll terminate the original query with a semicolon as before, then copy the result of the subquery select woot to the C drive in a file named offsec.txt. Because we don't need a time-based attack here, this request returns a response very quickly. All we have to do now is look at the root directory of the target C drive and see if the offsec.txt file has been created. Great. It appears that we've succeeded. Since we were able to write to the root of the C drive, we should at least have admin privileges on the server. We'll take a quick look at the properties of our new file. Amazing! Notice that not only are we running as DBA, but the web application is running under the context of the system user. Our proof of concept exploit is becoming more and more powerful. Let's continue. After demonstrating that we can write arbitrary files to the system, let's try to use this to our advantage and obtain shell access. While we could attempt to overwrite a batch file on the system, we discovered that ManageEngine executes VB script files, which makes for a more straightforward exploit vector. When we monitor remote servers and applications with the ManageEngine Applications Manager, we see that a number of VB script files are executed on a periodic basis. In order to make our installation a little more realistic, let's add a monitor to it and observe how and when VB script files are run. Let's open our browser and navigate to the application. We'll accept the certificate. Next, if we're not logged in, we'll use the admin credentials, username admin and password admin. We'll again close the dialog window. Great. Now that we're logged in, let's create a monitor by selecting New Monitor under the Monitors menu item. We'll create a monitor for the local Windows host. To do that, we select the Windows link under Servers. We'll enter the display name as ME Server, the host name as localhost, and in the OS type dropdown, we'll select Windows 2012. We'll add the username administrator and the password student lab. Make sure to check your lab material for the appropriate lab credentials. We'll set the polling interval to 1 minute to simplify monitor activity. Just to be sure that we entered the details correctly, we can click Test Credential. Great. Now that we know this works, let's click Add Monitor. We see a success status message and know that our monitor has been added. After some investigation, we discovered that adding this monitor causes ManageEngine to run VB scripts. To find out what scripts are run to support this monitor, we'll use the sysinternals process monitor. Process monitor displays real-time process activity, and after opening it, you'll see the display window fill up quickly. We need to filter out this activity and display only the items we're interested in. We can do this by clicking the filter icon. Then we'll choose the display entry path, the condition contains, and the term VBS. Next, we'll click the Add button and finally click OK. We may have to wait a few seconds to see any entries as our polling interval was set to 1 minute. Okay, great. Now that we have some results that match a path containing our term VBS, let's take a look. We notice that the process name is cscript.exe, which is a Windows operating system executable that allows scripts to be executed in a command line environment. In our example, the first VB script we see called in the ManageEngine application is Windows scripts.vbs, and subsequently wmi-get.vbs. Now that we know which VB script files are being executed by the ManageEngine application, let's attempt to overwrite them and execute malicious code. Of the two VB script files, we decided to overwrite wmi-get.vbs, simply because it has less content and as we'll soon see, a smaller file will make our life easier. Before we move forward, let's keep a few things in mind for our exploit. We're going to overwrite a file with its existing content and append our payload to it. For this reason, during our exploit creation, we'll make a backup copy of wmiget.vbs, as we'll need to restore it afterwards. The target file wmiget.vbs functionality is not necessarily important to us. However, we want to make sure that the original functionality of the script is maintained along with our payload, because we'd like to stay as stealthy as possible. We'll do this by taking the contents of our file and inserting our payload into a large one-line VB script entry. We have to do this because the Postgres copy-to function cannot process new line control characters. We'll also have to encode our payload twice. We'll use base 64 to avoid submitting special characters, and we'll URL encode the payload to ensure it does not get mangled. Another consideration when crafting this exploit is that a base 64 encoded payload will be quite large and can exceed the maximum URL length. For this reason, we'll change the request method from a GET to a POST. During our source code review, you may recall that when the servlet receives a POST, it's automatically passed as a GET in the servlet. Therefore, we can arbitrarily switch between GET and POST without losing functionality. Okay, let's start our exploit by looking at the wmiget.vbs file in Notepad++. When we look at this file, we notice the script accepts a number of arguments, as we can see in the case statement, and finishes with a wscript quit command. This command is an exit function, and anything we place after it will not run, so we'll need to keep that in mind as we create our exploit. As we mentioned earlier, we need this content to be collapsed into one line. Let's first save a backup of this file and then perform some find and replace on new line characters. Now that we saved a backup, let's open the original wmiget.vbs file again. Here, we'll make changes to this file and save them. Let's first remove the comment lines, as they would essentially comment out all the code on a single line. We can find these using regular expressions, searching for lines that have a single quote and have characters afterwards. We'll use Control F and search for a single quote .star. Once again, we have to select regular expression and clear the Replace With field. Just to make sure we're searching for and finding the right areas, we'll click Find Next and make sure we see the results we're looking for. Great, it looks like we highlighted the entire first command, so let's go ahead and remove all comments by clicking Replace All. Next, we need to remove the continuation lines. These are the ones with a space followed by an underscore. We can again use the Find and Replace command to remove these continuation characters. This one is kind of tricky, but let's start with the regular expression. We'll find each instance of a space followed by an underscore, which is followed by any number of characters, and finally a new line character. We also need to make sure that for this regular expression, we check dot matches new line to include new line characters. Let's click Find Next and see if we're selecting the underscore and a new line character. Great, it looks like we found what we want to replace, so let's click Replace All. Now, let's clear the dot matches new line option and continue on. The next pieces to replace are tabs in the code. We can find them by going back to our Find What box and entering a slash followed by the letter T as in tango. Again, we can click Find Next a few times to get a look at the tabs we're replacing and then click Replace All. Now we can use the Find and Replace command to get all this code on one line. We're going to find \n, which is a new line character, and replace that with a colon, which is a VBS command terminator. Great, Let's save our work. And we can test to see if the script still executes properly. We'll open a PowerShell window and navigate to the scripts directory where we have saved wmiget.vbs. Next, we'll use cscript to run wmiget.vbs. Excellent. We see that the script executed without returning syntax errors, and it's expecting command line arguments. When we first opened the script, we saw that it had a case statement based on the number of arguments passed, and the message we see was hard-coded in the script. Therefore, we can assume the script is working correctly as a one-liner. Next, we need to add a payload to this script, and we'll do that from our Kali machine. On our Kali machine, we'll use Metasploit's MSF Venom program to create a reverse shell encoded payload in the VBS format in which we specify the IP address and the port of our Netcat listener. Let's copy this payload and paste it into Notepad++. Here, we'll use a number of the same find and replace methods that we did previously with the wmiget.vbs file. We do not have comments, so we'll skip to continuation lines. Next, we'll replace tabs. Lastly, we'll replace new lines, but since we copied and pasted from our Linux machine, we'll find that we have a combination of carriage return and new lines to replace. We'll replace this combination with a colon as we did previously. One last tweak here is to find consecutive colons and replace only one. We'll likely have to click Replace All a few times. Great, now we can paste this into our wmiget.vbs file at the appropriate location. Looking at wmiget.vbs, we'll find our previous call out of the wscript quit statement. We'll paste our payload just before that statement and save. Now we can go back to our Kali machine, set up a Netcat listener on port 4444, and wait. Excellent, we have a reverse shell. We successfully edited wmiget.vbs to correctly work on one line and added our reverse shell payload to the same file. Now we need to go back to our attacking machine and use this one-line wmiget.vbs in our SQL injection. We'll paste our VBS one-liner into burp's decoder on our attacking machine. Now, let's encode it into base64 format. One thing we noticed when trying to only use base64 encoding is that we can see plus characters within the base64 encoded string. This will not be good for us, as these will be interpreted as a space character and break up our payload. One quick solution is to URL encode this payload, so let's try that. Excellent, now we can use this payload in our query. As before, we'll navigate to burp's repeater tab and start crafting our SQL injection payload that will overwrite wmiget.vbs. The first piece we need to craft is the SQL query that will decode our payload. That query looks like the following. We have spaces in our query, so we need to replace them with plus characters, or the submission of the user ID parameter will fail. We'll paste in our updated query with those spaces replaced with plus characters. Great, now we can go back to burp's decoder tab and copy our payload, which has been both base64 and URL encoded. This may not render well in burp, however copying and pasting the values works perfectly. Let's go back to our repeater tab and paste this payload in place of the encoded payload portion of our SQL injection. Excellent. Now we should be able to submit this payload by clicking Go. Okay, so something went wrong. We received a 400 bad request. Remember earlier when we mentioned this payload would be quite large? It turns out it's actually too large for a GET request, so we'll need to change to a POST request. We can do this easily in Burp by right-clicking in the request field and selecting Change Request Method. Okay, now that we have a POST request, let's submit it. Again, as is typical with this SQL injection, we do not receive much in the way of a response. But now let's open a terminal and configure a netcat listener with the L port value we used when we created this payload, port 4444. Remember that our polling time was set to 1 minute, so we should see a shell come back within a minute. Excellent. We use the copy to functionality to get a shell and obtain a reverse shell. A nice feature of this particular exploit is that it's persistent. However, the wmiget.vbs vector we used for this exploit is specific to the Manage Engine application running on a Windows host. Having a periodically executed application script that has been backdoored may not always be an option. Because of this, we may not want to rely on this exploitation technique and should consider another technique that could work on all Manage Engine deployments. Now that we've confirmed that we're operating under the context of the Postgres DBA and Windows system user, it may be possible to perform other actions that are even better than accessing the file system. For example, it may be possible to load a custom database extension that defines our own function. If that is possible, we can code anything we like in that function and have the database execute it for us. In other words, that would allow us to gain remote code execution directly. After looking at the Postgres documentation, we learned that it is possible to create and use custom functions through compiled extension files, in this case, DLL files. However, there's an important restriction that we need to keep in mind. The compiled extension we're trying to load must define an appropriate Postgres structure to ensure that a dynamically loaded object file is not loaded into an incompatible server. If the library that we're trying to load doesn't have this magic block, as is the case with all standard system libraries, then we won't be able to load it. Let's see how that looks in practice. We'll try to load the kernel 32 DLL into our Postgres instance and use it to create a custom Postgres function we'll call system. We'll use the following query. This query attempts to load the kernel 32 DLL's function winexec as the function system. As expected, the Windows DLL does not contain the specific Postgres magic block, and it's not loaded. Now that we've verified what the documentation states, it looks like we'll have to compile a custom dynamic library. While that may sound daunting, it's very much within our grasp. Let's do that now. To facilitate the development of our exploit, we've already installed a pre-configured Visual Studio 2017 build environment. Once you open Visual Studio, you should see a recent solution called AWAE. This will be our starting point for this section of the module. Let's start by opening up the AWAE solution and taking a look at the code. The template code in the poc.c file should include all we need to build a basic extension. It contains a few necessary include statements so that everything builds properly. Then, in this very simple example, we define a function called AWAE. We'll reference this function shortly during the creation of a user-defined Postgres function. If we look at the implementation of our function, we can see that it uses the Windows shell execute function to launch a process. The process we're launching is passed to the function as the first argument. We're also launching the given process in a for loop, which will create multiple instances of the target process depending on the number passed as the second argument. Although this example is rather trivial, it shows us how to deal with arguments passed to a function in a Postgres-specific DLL extension. Later on, this will help us avoid hard coding any of the values when we write our fully functional reverse shell function. Okay, we should be ready to compile this sample extension code. We can initiate the build process by pressing F7 within the virtual machine or by going to Build Solution in Visual Studio. It looks like everything compiled without errors. We can now move on to Postgres, where we'll use our newly created extension DLL file. In the last section, we created a trivial proof of concept Postgres extension that, when used, will launch a process of our choosing. We now need to see how we can use it within a Postgres database. In order to do that, we need to first create a custom Postgres function with the name of our choosing and link it to the exported AWAE function in the DLL we just compiled. Let's do that now. First, let's open up a command prompt and start PSQL again. We'll name our function test. Although Postgres allows function overloading, we're going to check to see if there's a function with the same name before we create one. We can do this with the command df-test. There is no function in the AMDB database named test, so let's use that function name. Now, for the ease of typing commands, let's copy the DLL extension file we just created to the root of the C drive. Okay, now we need to create a custom Postgres function named test, which will call the AWAE function exported by our DLL file. Notice that in the definition of this function, we're telling Postgres that it will accept two arguments, one of type text or string and one of type integer. Great, we can see that our function has been created. We'll test our extension code by launching 3 instances of the calc.exe process. Let's make sure that we have no calc.exe process already running before we launch our test. All right, the moment of truth is here. Let's execute the following query and see if our function works correctly. If this works, we should see 3 newly created calc.exe processes running in the background. Awesome, it's alive. Now we're going to make changes to the DLL, but we can't just modify the DLL and test the changes while it's loaded into memory. We'll need to unload the extension before performing any change to our code. First, we stop the Manage Engine service with the net stop command in a command prompt. Once the service has stopped, we'll delete the DLL file that we loaded while creating the test function. Now, start the service so we can go ahead and delete the test function. You'll likely have to restart PSQL. It does not exit automatically once the connection to the database service has been interrupted. We can use \Q to exit. We'll start PSQL again and verify that our function is still there by running \df-test. Finally, we'll execute the following drop SQL statement to delete our proof of concept function. Lastly, let's double-check the function was removed using df-test. As we've seen in the last section, Postgres allows us to create user-defined functions based on custom DLL files. There's also an interesting characteristic in this process that's worth mentioning. In the previous case, we conducted our proof of concept attack entirely on the target machine. In other words, we've loaded the extension from a local drive, but in reality, we're not limited to local resources only. Postgres actually allows us to create user-defined functions based on extension files that are located on network shares as well. Let's make a quick Samba share on our Kali attack machine using a Python impacket script. We'll grab the attacking IP address and start the service. Let's open a command prompt and grab the attacking IP address with ifconfig. We'll also make a directory called AWAE where we'll run our Samba share. We can now start the Samba server. Good. These commands helped us set up a Samba share on our attack machine named AWAE, sharing the directory home Kali AWAE. Now that we have that running, let's use it to copy our DLL to the attacking machine. Then we'll load it just as we did before, but this time using the network share path as our source. We'll switch to our Manage Engine server and open Windows Explorer. Let's navigate to the DLL that we built, which is located in the AWAE release folder, and we'll copy the AWAE DLL. Now we'll navigate to our Samba share on the attacking machine by browsing to 192.168.119.9/AWAE. Lastly, we'll paste the AWAE DLL here. Now, let's open our PSQL terminal and create our function as we did before, but this time we'll reference the DLL file on the Samba share. We'll issue the following query. Since we're going to test the function by spawning calc.exe, let's once again make sure that we have no instance of calc.exe already running on our system. We can do this with PowerShell like we did earlier. We do see that we have instances of calc running, so we'll kill them with the task kill command by using the force and name flags. Now, let's verify we removed all the calc.exe processes one more time. That looks good. Now, let's execute our query from the last example again and see if it launches calc.exe as expected. We'll run the query, select remote_test, and send the parameters calc.exe and the number 3. That looked successful. Now let's open PowerShell again and check to see if we now have 3 calc.exe processes running. As we can see, loading Postgres extensions from a remote share works just as well. Now let's get a reverse shell. It turns out that the only sanitization of the JSON request is done through the regular expression we saw earlier, which checks for a valid item format. Let's go back and look at the regular expression once again. We'll reopen lib batch.js, and we'll jump to line 23, where the regular expression is defined. In order to interpret and understand this regular expression, we'll use a website that provides a regular expression testing environment. Let's copy our regular expression from the batch.js file to the regular expression field in our browser. Inside the test string field, we will use a known valid string from our original payload with a small modification. The forward slashes are essentially used as a string separator, and the strings between the slashes are then grouped using the dot character as a separator, but only if the digit pattern is matched. In this case, when we injected ;hacked into our initial payload, we managed to successfully pass the regular expression checks. Because the semicolon character is used to terminate statements in JavaScript, we should be able to append code to the original post request and execute it. To confirm this, we'll use the log method from the Node.js util module and print the message hacked to the console. Before doing this, let's quickly test it against the regular expression checker to make sure it will work. Our entire payload is grouped within group 2, which means that we should be able to reach the eval function and our payload should execute. Rather than hard-coding the payload in our proof of concept, we updated it to build the JSON payload and append code of our choosing to the last request entry. Let's use a simple log function as our payload and try to execute it on our target machine. The reply we get back from the endpoint does not seem to have changed. However, switching back to the Node.js server confirms that we have indeed successfully executed JavaScript code on the target. Excellent! We can execute arbitrary JavaScript code on the server, but a simple log function is not really what we're looking for. Ideally, we want to execute a shell on the target. One interesting thing to note is that the regular expression isn't truly sanitizing anything. It's simply making sure that the user-controlled input is well formatted. Now that we can remotely execute arbitrary code on the target through the Bassmaster vulnerability, let's try to inject a JavaScript reverse shell into our JSON request to wrap up our attack. First, let's take a look at one of the many publicly available JavaScript reverse shells. The code of our reverse shell is more or less self-explanatory. It redirects the input and output streams to the established socket using the Node.js net module. Let's take a look at the next proof of concept code that includes the reverse shell. We modified the code slightly to allow us to pass the attacking IP address and port as arguments. Before executing our new proof of concept, we need to have a netcat listener ready on our attacking Kali machine. Let's set that up now. We'll configure our netcat listener on port 5555. With the listener up and running, we can now proceed to run our proof of concept. Rather than the usual response from the server, this time we receive an error. If we look at our netcat listener, we see that no connection has been received on our attacking Kali machine. In order to troubleshoot this issue, we'll slightly modify the JavaScript code in lib-batch.js on the target server and add a single debugging statement right before the eval function is called. We're mainly interested in what is passed to the eval function for execution. Let's stop the current Node.js web server instance using Control-C. Using Nano, we'll open batch.js and go to line 152 using the Control_ keyboard shortcut. We want to see what is being passed to the eval function, so we'll use the log function to print the arguments to the console. We can save the file now and restart the Node.js web server instance. Now we'll execute our proof of concept once again and inspect the output on the server side. Interesting, it appears that our payload is being truncated at the first /. Let's copy our payload to the clipboard, and we'll submit it to the regular expression checker to see how exactly the parsing takes place. As we can see, the regular expression is explicitly looking for / and groups the input accordingly. This makes sense because the Bassmaster plugin expects URL paths as input. In order to execute our reverse shell, we need to think of a way to overcome this character restriction. Fortunately, JavaScript strings can be composed of hex-encoded characters, in addition to other encodings. We should be able to hex encode our / and avoid the regular expression parsing. All that's left now is to execute it and test our new payload. Remember that our netcat listener is still running on port 5555 from our previous failed attempt. This time, we do not receive an error as the response, so let's check our listener. It seems our netcat listener has received a connection. Excellent. We were able to successfully analyze the Bassmaster source code and identify the vulnerability, understand how to reach it from the perspective of a remote attacker while dealing with character restrictions. Our analysis ultimately enabled us to obtain a reverse shell on the target machine. .NET Nuke Cookie Deserialization Remote Code Execution. In this module, we'll introduce data serialization and deserialization and explore how improper implementation of object deserialization in .NET can create various vulnerabilities. We'll also dive deeper into the analysis and exploitation of a publicly known vulnerability in the .NET Nuke platform. To begin, let's discuss the basics of serialization. At a very high level, serialization is the process of converting structured data into a format that can be stored in a file or transmitted over a network link. Generally, serialization involves a producer and a consumer of a serialized data structure or object. In modern object-oriented programming languages, the producer application is able to define and instantiate an arbitrary object, modify its state, and then either store it in an appropriate file or send it over the network. As long as the format of the serialized object is understood by the consumer application, the object can be recreated in its process space and further processed. Serialized objects in .NET can be stored in various formats that are handled by different classes, depending on the selected format. For the purposes of our example, we'll focus on the XML serializer class, as it is directly related to the vulnerability covered in this module. As the name suggests, the XML serializer class stores the state of an object in XML format. To get a full understanding of the specific capabilities and limitations of the XML serializer class, we recommend that you read the full article. For now, however, we'll focus on a few limitations that will play a role in our analysis. First, the XML serializer class can only serialize public fields and property values of an object. Additionally, the class supports a narrow set of object types, primarily due to the fact that it cannot serialize abstract classes. Finally, the type of the object being serialized always has to be known to the XML serializer instance at runtime. If we attempt to serialize or deserialize object types unknown to the XML serializer instance, the code execution will fail with a runtime exception. For our first example, let's create two simple applications. One application will create an instance of an object, set one of its properties, and serialize it to an XML file using the XML serializer class. The second application will read the file containing the serialized object and deserialize it. The source code for the application is available on your .NET Nuke lab machine. To begin, let's connect with our desktop. The serializer application source code is in the default Visual Studio project path. Let's briefly walk through the code. Our namespace contains an implementation of the myConsoleText class starting on line 26. This class prints the string value stored in the private text property to the console when its public counterpart is set. We create an instance of the myConsoleText class and set its text property on lines 11 and 12. On line 19, we create an instance of the XML serializer class, serialize our myText object, and save it to basic.xml.txt on line 21. Now that we understand what our producer application does, let's look at the source code of the consumer application. The deserializer application creates an instance of the XML serializer class using the myConsoleText object type and proceeds to deserialize the contents of the input file into an instance of the original object. Since the application does not have the myConsoleText class defined within its namespace, we need to instruct our application to use the basic XML serializer namespace, which we can see on line 3. The reference to the basic XML serializer assembly file should already be added to your project. Finally, we compile both applications using the Build Solution option from the Build menu. With both applications compiled, let's run our serializer application, passing a string as an argument at the command line. Good. Let's take a look at our serialized object, which should be stored in XML format. Now we can try to deserialize our object by running basic XML deserializer.exe. As an argument, we will pass the path to the basic XML.txt file, which contains our serialized object. The generated hello-AWAE output is the result of the execution of the code defined in the myConsoleText property setter method. Notice how the setter of our property was automatically executed during the deserialization of the target object. This is an important concept for an attacker. In some cases, by using properties, the setter can be used to trigger the execution of additional code during deserialization. If we take a look at our basic XML.txt file, we see that we could easily modify the contents between the text tags to display a different message during object deserialization. We'll demonstrate this later on in our next example. While this example is very trivial, it effectively demonstrates how XML serialization works for .NET. Let's expand on this example a bit further. Our previous example was quite rigid in that it could only deserialize objects of the myConsoleText type, because that was hard-coded in the XML serializer constructor call. A developer could make the custom deserialization wrapper a bit more flexible and provide it with the ability to deserialize multiple types of objects. Let's look at one possible way to achieve this. The following examples borrow heavily from the .NET Nuke codebase, which will help streamline our analysis later on. Rather than serializing a single type of object, we've given our application the ability to serialize an additional class called mySecondConsoleText, starting on line 59. Looking back at the main function, the appropriate class is instantiated based on the user-controlled argument passed on the command line. This can be seen on lines 15, 17, and 23. The most significant and interesting changes to the application are contained in the custom serializer function. On lines 34 to 35, we pass the information about the type of object being serialized in a custom XML tag called item. Notice that we are no longer hard-coding the type of the object we are serializing during the instantiation of the XML serializer class. Instead, we are calling the getType function on the target object in order to dynamically retrieve the type information. Finally, the serialized object is wrapped inside a custom-created XML document and written to disk. Let's review the corresponding deserializer application. We now have to take into account that our serializer example has two different serializable classes. This means that the deserializer application has to be aware of those classes so that the XML serializer instance can properly process the objects at runtime. Since we're not directly instantiating instances of the classes, we don't need to include the using multi-XML serializer statement in our code. Nevertheless, we still need to have a reference to this assembly in our Visual Studio project, since the application still needs to know what the dereferenced object is. The most interesting part of our deserialization application is how it dynamically gathers information about the type of the serialized object from the XML file and uses that to construct the appropriate XML serializer instance. Let's build both applications, starting with the serializer. Now, we'll build the deserializer. Next, let's run the applications and see what effect our changes have. Looking at the generated XML file, we see that we now have our custom item node which contains the object type. Finally, let's see what happens when we deserialize this object. In our previous example, we discussed how it was possible to change the text property directly in the XML file in order to print a different output once the object is deserialized. Let's try to take this further. Instead of deserializing one instance, my first console class, let's try to alter the serialized object and force the deserialization of an instance of my second console class. Let's open the output XML file and try this out. We'll replace every instance of my first console text with my second console text, then save the modified file and run our deserializer application again and check out the result. Excellent, it works. In this example, we had access to the source code and could easily gather the required information about the object. However, we could have achieved the same result without the original source code by decompiling .NET modules using publicly available tools. Next, let's complete our example and show how a deserialization implementation like this can be abused. Consider the following changes to our multi-XML deserializer application. In the new version of our deserializer application, we kept the original code intact and simply added the implementation of the exec.cmd class. As the name suggests, this class will spawn a new process based on the private property CMD. This private property is set using the value that's been assigned to the public CMD property of an exec.cmd object instance. Next, the setter function makes a call to the exec command function, which starts a new process using the private CMD property value. Based on our previous example, we already know that we can manipulate the content of a properly serialized object file. This can trigger the deserialization of an object type that falls within the parameters of the XML serializer limitations. In this example, the exec.cmd class does not violate any of those constraints. From an attacker's perspective, we can attempt to change the previously generated XML file and modify the object from a mySecondConsole class type to exec.cmd type. Notice that in the modified XML file, we also have to change the text tag to a CMD tag in order for it to correspond to the public property name used by the exec.cmd class setter. Finally, we've set the tag value to calc.exe since this is the name of the process we want to initiate. Now we can save the modified XML file and rebuild our deserializer. Let's try to execute our deserializer application again and inspect the result. Excellent. We managed to spawn calc.exe by tricking the target application. As long as we're able to retrieve the class information we need and the target class can be deserialized by the XML serializer, we can instantiate objects that were not intended to be deserialized. This is possible because object type verification is not implemented in the code we've analyzed so far. The application blindly trusts a user-supplied input and processes it using the XML serializer class. In real-world cases, this type of vulnerability can have critical consequences, as we'll soon see. Now that we've gathered some basic knowledge of the XML serializer class, we can start analyzing the .NET Nuke vulnerability. The public advisory reported the vulnerability in the processing of the DNN personalization cookie. As the name implies, this cookie is directly related to a user profile. What's interesting, however, is the fact that this vulnerability can be triggered without authentication. Now that we've gathered some basic knowledge of the XML serializer class, we can start analyzing the .NET Nuke vulnerability. The public advisory reported the vulnerability in the processing of the DNN personalization cookie. As the name implies, this cookie is directly related to a user profile. What's interesting, however, is the fact that this vulnerability can be triggered without authentication. The entry point for the vulnerability is found in the function named loadProfile, which is implemented in the .NET Nuke.dll module. Even though the source code for DNN is publicly available, for our analysis we'll decompile the target DLL using dnspy. These debugging skills will also help us trace the execution of our target program later. Let's open the .NET Nuke assembly in dnspy. With the file opened, we can navigate to the vulnerable load profile function in the .NET Nuke Services Personalization Controller namespace. Before we analyze the load profile function, it's important to note that the researchers who discovered the vulnerability revealed that this function can be triggered any time a user visits a non-existent page within the web application. We'll confirm this later on. For now, let's take a look at the decompiled code. Starting on line 24, the function checks for the presence of the DNN personalization cookie in the incoming HTTP request. If the cookie is present, its value is assigned to the local string variable called text on line 26. On line 29, this variable is passed as the argument to the deserialize hash table XML function. We can follow this execution path by clicking on the function in dnspy. The deserialize hash table XML function acts as a wrapper for the deserialize hash table function. This function accepts two arguments. The second argument is the hard-coded string profile. We'll take note of this as it will be important for the development of our exploit. We can continue to follow this execution path by clicking the deserialize hash table function. In our earlier XML serializer examples, we borrowed heavily from the DNN codebase in order to demonstrate some of the pitfalls of deserialization. Because of this, the structure of the deserialize hash table function should look very familiar. In our particular case, this function is responsible for the processing of the DNN personalization XML cookie. On line 156, we enter a for each loop that iterates over every item node under the profile root XML tag. On line 160, the function extracts the serialized object type information from the item node type attribute and creates an XML serializer instance based on the extracted object type information on line 161. Finally, the serialized object is deserialized on line 163. It's important to note that so far we haven't seen any checks on the input object type during deserialization. This means that if we're able to reach this function through a request crafted with an appropriate serialized malicious object, we may be able to control the execution flow. This looks promising, but before going further, we need to set up our debugging environment, which will allow us to properly follow the application execution path while processing our malicious cookie values. Due to various optimizations that are applied to the executable at runtime, Debugging .NET web applications can sometimes be tricky. One of those optimizations affects debugging sessions by preventing us from setting breakpoints at arbitrary code lines. As a consequence of this, in addition to not being able to set a breakpoint where we want, at times we're also unable to view the values stored in local variables that exist at that point. Fortunately, we can modify the optimization of the executable at runtime by changing the assembly attributes of the target executable and recompiling it using dnspy. But first, we'll create a backup of .NET-nuke.dll. Now, we'll switch back to dnspy and access the .NET-nuke.dll attributes by right-clicking on the module name in the Assembly Explorer window. We're mainly interested in the debuggable attribute. We can disable optimization with a simple modification. Refer to your lab guide for more information on these debugging flags. Once we've made the changes, we can recompile by clicking Compile. Finally, we'll save our edited assembly. We can do this from the File menu. It's important to note that once the IIS worker process starts, it will not load the assemblies from the .NET-nuke directory in the inetpub path. Rather, it will make copies of all the required modules for DNN to function and load them from a temporary directory. In order to make IIS load the edited module, we can simply restart the service. We'll once again rely on our burp proxy to precisely control our payloads, while using the dnspy debugger to see exactly how they're being processed. In order to properly debug our vulnerable application, we need to first attach our debugger to the w3wp.exe process. This process is the IIS worker under which our .NET-nuke application is running. In order to ensure that an instance of w3wp.exe is running, we first need to perform an HTTP request to the target application, which we can do by simply browsing the .NET-nuke homepage with a web browser. Our browser is already set up to use a proxy, so we need to make sure we start burp before browsing to the .NET-nuke instance. We will use some of the intercepted requests later on. As we previously mentioned, the IIS worker process copies all necessary assemblies from their original location into a temporary directory and loads them from there. In order to ensure that we are working with the correct assemblies in dnspy, we will first close the open assemblies. Then, to load the correct modules and be able to set breakpoints, we need to first attach to our process. With the debugger attached to our process, we'll pause execution from the debug menu and list all the modules loaded by the w3wp.exe process. In order to easily access and decompile any .NET-nuke class we're interested in, we can load all the available modules in the Assembly Explorer pane. This is done by right-clicking any module and selecting the Open All Modules context menu. This process may take a few seconds due to the rather large number of modules that are loaded by the w3wp process. We'll start by sorting the loaded assemblies and then navigate to the vulnerable load profile function located in the personalization controller namespace. Once there, we set a breakpoint on line 24 where we started our initial analysis. With the breakpoint set, we're finally ready to send our first proof of concept HTTP request. We can use one of our captured unauthenticated requests from our burp history and then send it to the repeater tab. Here, we'll add the DNN personalization cookie and also change the URL path in the request to a non-existent page. The content of the cookie is not important at the moment since we're only trying to validate our debugging setup. We'll use a simple placeholder value for now. We'll click Go to send the modify request, and if everything goes according to plan, we should hit our breakpoint in DNSpy. Excellent. We've reached the target function and have verified a part of the original advisory. So far, we have trusted the original advisory blindly, and we're able to validate the fact that we can trigger the load profile function. However, it is highly unusual to see any sort of personalization data being processed from an unauthenticated request. Because of this, it's worth investigating other functions called during the processing of the HTTP request that triggers the vulnerability. A good place to start our analysis is the call stack, which we can see by clicking on the relevant call stack tab at the bottom of the DNSpy window. If we look at the rather large call stack, we notice the usermode.get method of the portal settings class invoked just a few functions before our breakpoint. Let's take a look at the implementation of this function. We can see that the call to the personalization.getProfile method, which is the next entry in the call stack, is located on line 925. We'll set a breakpoint on line 926 and resend our proof of concept request in order to verify that we can reach this call. Notice that our breakpoint, which we've managed to hit as part of the processing of the unauthenticated request, is located inside an if statement. Looking at the if statement, we see that one of the conditions is a check of the isAuthenticated Boolean. This is very peculiar, as we clearly are not using any authentication or session cookies in our proof of concept, yet our request is treated as authenticated. In order to figure out why this is happening, we need to go even further back in the call stack. Here we see a call to a function named advanced URL rewriter.handle 404 or exception. Let's have a look at it by clicking on its call stack entry. Although the implementation of this function is rather long and complex, we're mainly concerned with the instance where the HTTP context.user property is checked. According to the code, if the user property of the request is null, then it gets assigned the value of the current thread user. In order to get a better picture of the consequences of this execution path, we'll set a breakpoint on line 809. To trigger this breakpoint, we go once again to the Repeater tab in our burp application and resend our initial proof of concept. Once our breakpoint is hit, we can switch to the Locals tab in DNSpy and check the values stored in various properties. If we take a look at the user property, we confirm that it is indeed null and execution enters the if branch. Additionally, we can also check the context request is authenticated property to check the authentication status. Before proceeding, we set a breakpoint on line 813 and let the execution flow continue. Once the breakpoint is hit, we inspect the context user and the isAuthenticated properties once again. As we can see, the request seems to be authenticated under the IIS app pool group. The reasoning for this logic seems to lie in the fact that the 404 handler is invoked before the HTTP context user object is set. Since the continued processing of the given request depends on the isAuthenticated property, the developers are making sure that no null references will occur. They do this by setting the user object to the Windows principal object of the currently running thread. Even if this information is not essential for the exploitation of our vulnerability, it's always good to gain a firm understanding of the code flow before proceeding. Now that we've completed the analysis of the vulnerability and have a working debugging environment, we need to start thinking of how we can exploit this vulnerability. As we're dealing with a deserialization vulnerability similar to the examples covered at the beginning of this module, our goal now is to find an appropriate payload object for our request. As a reminder, our object will need to have the following characteristics. It needs to execute code which we can use for our purposes. It needs to be present in one of the assemblies loaded by the DNN application. It needs to be serializable through the XML serializer class. And finally, it needs to be serialized with the appropriate XML format the vulnerable deserialize hash table function expects. The original advisory suggests the file system utils class available in the .NET Nuke DLL assembly as a payload choice. This class implements a method called pullFile, which we can easily locate using dnspy. This function could prove to be very useful as it allows us to download an arbitrary file from a given URL to the target system. Take note of the arguments passed to this function. We'll need this information later. If we could trigger this method using the DNN personalization cookie, we could theoretically upload an ASPX shell and gain code execution on our target. The issue, however, lies in the limitations of the XML serializer class. While the file system utils class is within the DNN application and would therefore be known to the serializer at runtime, the XML serializer cannot serialize class methods. We can only serialize public properties and fields using the XML serializer class. Unfortunately, the file system utils class doesn't expose any public properties that we could use in order to trigger the invocation of the pullFile method. Because of this, we need to take a different approach. The security researchers who discovered this vulnerability also disclosed a handful of .NET deserialization gadgets. These gadgets are classes that can facilitate malicious activities during the user-controlled deserialization process. One of the disclosed gadgets is named Object Data Provider and is arguably the most versatile. It was also the gadget the researchers used in their demonstration of the DNN exploitation. Before proceeding with the exploitation process, we need to take a deeper look into this class. Looking at the official documentation, this class is used to wrap another object into an Object Data Provider instance and use it as a binding source. A binding source is simply an object that provides the programmer with relevant data. This data is then bound from its source to a target object, like a text box, to display the data. This class enables us to wrap an arbitrary object and use the method name and method parameters properties to call a method from a wrapped object and pass the necessary parameters to it. In short, we could use the Object Data Provider properties to trigger method calls in a completely different object without violating any limitations of the XML serializer class. In order to get a better understanding of the mechanics involved, we should analyze the gadget's entire code execution chain. The Object Data Provider class is defined and implemented in the System Windows Data namespace of the Presentation Framework .NET module. Our Windows system has multiple .NET frameworks installed. However, for our purposes, we can use the Presentation Framework assembly from .NET version 4. Let's open this DLL in dnspy and navigate to the Object Data Provider class. Now that we have the correct DLL decompiled, we can inspect the Object Data Provider method get and set implementations. We can see that when the method name property is set, the private method name variable is populated and the base refresh function is called. If we trace this call, we end up at begin query, which seems to be a dead end. However, we need to remember that the Object Data Provider class inherits from the Data Source Provider class, which is where the debugger took us. Because of this, we need to make sure we navigate to the begin query function implementation within the Object Data Provider class that overrides the inherited function. At the end of this function, we find another function call named query worker. Finally, on line 300, there is a call to the invoke method on instance function. This is where the call to the wrapped object method actually begins. This is only vaguely apparent from our static analysis, so we'll confirm this with dynamic analysis. Let's leverage a simple Visual Studio application to trace the execution of the Object Data Provider gadget. For simplicity, we'll reuse as much of the existing DNN code as possible and add references to .NET-Nuke.dll and presentationframework.dll. We also need to set up a web server on our Kali machine from which we can test the download of an arbitrary file using the pull file gadget. Let's create a test file in the web root and start Apache. We'll tail the Apache log file to monitor our web requests. With the setup out of the way, let's go back and take a look at our code. The application starts by specifying the appropriate namespaces. Starting on line 13, we create an Object Data Provider instance. Then we instruct it to wrap a DNN file system utils object and set the method name to the pull file method. Finally, we pass the appropriate parameters to the method. The first parameter points to the remote file on our Kali machine, which we have to adjust based on our IP address. The second parameter sets the path where the downloaded file will be saved. Notice that we're using the DNN web root as the destination directory. This will become useful later on in our attack when we access our web shell through a browser session. Let's build our application. This time, rather than attaching to an already running process, we'll directly start our application from within the debugger and set a breakpoint on the entry point. Once we click OK, our application should start and we should hit the breakpoint inside our debugger. We'll navigate directly to the query worker function inside the presentation framework assembly in order to verify the analysis we performed earlier on the Object Data Provider class. Here, we want to set a breakpoint on the function call invoke method on instance. If everything works as expected, once we let the execution flow continue, we'll hit our breakpoint. Excellent. If we look at the call stack window in dnSpy, we can see that the code execution occurred exactly as expected according to our analysis. One thing to notice is that if we let the execution of our process continue, we'll once again hit this breakpoint. We'll actually hit this breakpoint 3 times, once for each time we manipulate values related to the Object Data Provider instance. The first time, we hit the breakpoint when we set the method name property. The second and third times, we hit the breakpoint when we set the method parameters for the function call. As an exercise, you can verify this process on your own. After hitting the breakpoint 3 times, if we continue the execution of our application, we should see an entry in our Kali web server logs indicating the successful invocation of the pull file method. We can further validate that our file has indeed been downloaded by browsing to the .NET Nuke web root in File Explorer. So far, we've been able to demonstrate that an instance of the Object Data Provider class can trigger the File System Utils pull file method if used appropriately. The next thing we have to do is attempt to serialize this object and verify that we can trigger the same chain of events during deserialization. We know that our DNN personalization cookie payload has to be in XML format. Since we've already demonstrated how to serialize an object using the XML serializer class in the previous example, we can add that code to our Object Data Provider test application. We'll then use this application as the basis for our final serialized payload generator. One important thing to remember is that based on our analysis, the DNN personalization cookie has to be in a specific XML format in order to reach the deserialization function call. Specifically, it has to contain the profile node along with the item tag, which contains a type attribute describing the enclosed object. Rather than recreate this structure manually, we can reuse the DNN function that creates the cookie value in the first place. This function is called Serialized Dictionary and is located in the XML utils namespace. Let's reopen the .NET Nuke assembly and take a quick look at this function. As we can see, the function builds the XML document using a specific structure that contains the item elements along with the type attributes, which we've already encountered in the deserialize hash table function. Now let's take a look at our adjusted application, which contains the call to the serialized dictionary function. On line 20, we start by creating a hash table instance and then add an entry called myTableEntry, to which we assign our Object Data Provider instance. We then use the serialized dictionary function to serialize the entire object while providing the required profile node name and prepend the cookie name to the resulting string. Finally, we save the cookie value to a file. Let's compile our application and run it using dnspy. Unfortunately, we receive an error message. Let's hit OK and dig a bit deeper into the exception. It appears that the serializer did not expect the file system utils class instance. If we look back at the serialized dictionary function, we see that our error occurs because of the way the XML serializer class is instantiated. The XML serializer instance is created using whatever object type is returned by the getType method on the object passed into the function. Since we're passing an Object Data Provider instance, XML serializer expects this type. The XML serializer will have no knowledge of the file system utils object type that is wrapped in the Object Data Provider instance, and this causes the serialization to fail. Because of this, we need to consider a different wrapper object to achieve our goal and invoke the pull file method. The vulnerability researchers suggested the use of the expanded wrapper class as a workaround. Your lab guide contains a more detailed description of this class. For now, however, we will only focus on the constructor and how it can help us achieve our goal. The expanded wrapper class represents a generic object type. Most importantly for us, the constructors of this class give us the ability to specify the types of the object that are encapsulated in a given instance. The expanded wrapper class represents a generic object type. This helps us overcome the issue we encountered while attempting to serialize the object data provider object. Let's see how this will look in our application. This code chunk shows how we can wrap our source object data provider object into a new object type and provide the properties we need, such as the method name and method parameters. Specifically, on line 18, instead of using the object data provider directly, we're now instantiating an object of the type expanded wrapper. On line 19, we use the expanded wrapper generic property projected property 0 to create an object data provider instance. On line 20, we create an instance of the file system utils class and then specify our target method as we did in our previous example. On line 22, we need to enter the IP address of the attacking machine. The remainder of this code is identical to our earlier code, in which we reuse the serialized dictionary function to store our serialized object in an XML document. Once again, in this case, we're attempting to serialize the expanded wrapper properties rather than methods in order to satisfy the XML serializer class limitations. Once we build and run the executable, we should no longer encounter any exceptions, and the program will successfully complete the serialization process. So far, so good. Our web server logs should show the corresponding HTTP request. Finally, let's make sure that our file was written to the .NET Nuke web root directory. Excellent. This approach appears to be working. Let's also take a quick look at the XML document that now should contain our serialized object. As we can see, this time the serialization process completes successfully, thanks to the extended wrapper class, which allows us to explicitly provide both of the object types we're trying to serialize. Finally, we need to make sure that our serialized object can be properly deserialized within the DNN web application. We can quickly test this by modifying our example application to emulate the vulnerable DNN deserialization process. Specifically, we'll feed the XML file generated from our previous example to the deserialize hash table XML function. We hard-coded the path to this file in our example code. On line 19, we've implemented a simple deserialize function. This function reads the serialized expanded wrapper object we previously created and attempts to deserialize it with the same function we saw in the vulnerable load profile call. Let's attempt to run the compiled application under dnspy. Recall from our earlier analysis that the wrapped target method we would like to execute is triggered by the object data provider invoke method on instance function. A deeper inspection reveals that the actual method invocation happens using the invoke member function call within the invoke method on instance function. We'll use this as the location for our breakpoint. Once we continue the execution and our breakpoint is hit, we can check the call stack to confirm that the deserialization is proceeding as planned. If we delete the breakpoint by right-clicking on it, select Delete Breakpoint from the pop-up menu and let the application continue the execution flow, we should see our file download once again. Now that we're able to successfully construct a working payload, it's finally time to put everything together and test it against our DNN server. Our plan is to gain a reverse shell on the target using this vulnerability. In order to do that, we'll use an ASPX command shell from our Kali machine. This web shell file will allow us to execute arbitrary operating system commands once we manage to place it on the vulnerable .NET Nuke server. We'll copy the shell to our web root and make sure we set the appropriate permissions. We'll once again use our application to serialize the expanded wrapper object, making sure to update our URL and the file name. Let's build our new application. Now we'll locate it and run it to generate the new XML payload. The resulting serialized object should look like this. Let's also make sure that our web shell file has been downloaded to the .NET Nuke web root directory. Now that we've verified that everything worked as planned, we'll delete the web shell file and perform the actual attack by using the generated serialized object in an HTTP request. We'll modify the request we initially sent to trigger the vulnerability. This time, however, we'll assign our serialized payload to the DNN personalization cookie. Remember, we can write to the DNN root directory thanks to the IIS account permissions applied and required by the DNN installation instructions. Everything should have worked as planned, and our malicious payload should have executed as expected. We can confirm this by looking at the web server log file. Finally, we can validate our attack success by browsing to our newly uploaded web shell. Nice. At this point, we can execute any command of our choosing. We'll use PowerShell to execute a reverse shell on the target. In order to avoid issues with quotations and encoding while passing this command into the web shell, we'll use base64 encoding and the PowerShell encoded command parameter. We'll copy this payload to the clipboard and set up our netcat listener on port 4444. Next, we'll execute our payload in the web shell. Excellent. We have a reverse shell. Our exploit is finally complete. This module covered the analysis and exploitation of a deserialization vulnerability in the .NET DNN application. These types of vulnerabilities are most often found in PHP or Java-based applications. However, as we've demonstrated in this module, .NET applications can suffer from this vulnerability class as well, and the impact can be significant.